started my PhD that this will happen. And so I worked for like 12, 15 years with him and his group. And during that time, we worked mainly on attosecond pulse generation and attosecond spectroscopy. So if you want to generate attosecond pulses, which are very, very short pulses, it's 10 to the minus 18 second, you need very powerful lasers, right? So then big part of our tasks was on development of the lasers. Then we worked on a very specific type of laser technology, which are called ytterbium YAG thin disk lasers. This is a kind of lasers that I'm going to talk about them in my lecture a lot, right? That you learn about the technology. And then we showed that you can generate very short pulses from these lasers. You can also, go to very exotic wavelengths like mid-infrared and terahertz. And then we also showed that you can measure the electric field of light at very high frequencies in ambient air with this kind of lasers, right? So this is like having an oscilloscope in the lab that you can just detect the light with. Then I moved at one point to Erlangen. This is how our institute looks like. Some people say that it looks like a big printer, but okay. Do you think it's like a big printer? Okay, well, it's a very beautiful building. It's very new. And there I have, in my research group, we are following some research. One of them is to use this kind of laser pulses that we generate for biological imaging and spectroscopy, which we call it femtosecond fieldoscopy. So we also look at the interaction of very intense light with matter, and we develop solar lasers. I'm going to talk about solar lasers tomorrow. These are important, and we have to all work on them to just push the frontiers of solar lasers. We also do a bit of gas spectroscopy, for example, to monitor the air pollutants and stuff like this at the mid-infrared region. So today I'm going to talk to you about how to generate femtosecond and attosecond pulses, and tomorrow we go to the, okay, let me go back. So tomorrow then, at the end, I talk a bit how to develop a solar laser, for example. So just to give you an impression, what is the meaning of a short pulse, right? I would like to show you this video. This is a part of documentary from BBC, right? BBC has these very nice documentary videos. And this is a research that some scientists did to understand what are the acoustic waves, how they look like when a bird is flying in air, right? What is the shape of these acoustic waves that they are generated through this flying bird? How the experiment is done? So the scientists have like three kinds of birds: a pigeon, an eagle, and an owl. And then they have very sensitive microphones on the ground. And then they push the birds to fly over these microphones, and the microphones just detect the acoustic waves which are generated in the air. Okay? So let's look at the results. It's very impressive. So the first bird is a pigeon. Now it flies over these microphones here, and you can see it generates these multi-cycle pulses, right? The second one is an eagle. It flies over the microphone, and it generates these very short pulses, which you can call them also light transient, right? And the third one I just show you because it's beautiful. It's an owl, right? This is a night owl, and they are hunters of night, right? It flies over the microphone, and it doesn't generate any wave. That makes them very successful in hunting at night, right? Because the other animals, they don't recognize that they are coming to them. So why different laser pulses matter? Why do you want short pulses? It's about how you can interact with matter, right? So if you have a shorter pulse or more intense pulse, you can have a more nonlinear interaction with matter. So these scientists who worked on birds, they were, I think in heart, they were like optics scientists because they continued the experiment. And what they did they remove the microphone, and they just put feather on the floor. So feather is like matter, right? And let's say these acoustic waves are like optical waves. And then they just push the birds to fly over the feather. And they looked how these waves and matter interact with each other. So let's look and see. Maybe you can press the video to run. Okay, it's running. That's okay. So now the pigeon with the multi-cycle pulses fly over the feather, and then you can see you have a very chaotic coupling to matter, right? The feather is just excited, and then it's chaos. Now the eagle flies. If you let me just go back, that I can talk about you better on this. Now it's fixed, right? The voice? Okay. So now the eagle flies, and you can see. You cannot see anything at the moment. Okay. So I just press. Right. So let's look at it together again. So when the pigeon flies with these multi-cycle pulses, you cannot excite the matter very well. The amplitude is small and it's very chaotic, right? You just randomly excite the feather from the floor. And now the eagle with this few cycle or light transient flies over, and then you can see you have very high amplitude. You can excite the matter with a high amplitude, and you can have localized excitation, that they are less chaotic. And then the last one, you know what to expect, right? So the last one is when it's beautiful, right? How they're just shaken because of the precision of the light. And the night owl now flies, and you can see that it flies very smoothly over the feather, right? And it just doesn't have any interaction because it doesn't generate any pulses. So these two types of pulses are the type of laser pulses that I'm going to talk to you about, how to generate them. Let me go to the next slide. Okay. So now today I'm going to talk to you about how to generate intense pulses. Intense means that they have so much energy, right? And if you shine it to matter, then you change the matter, right? And then I'm going to talk first about generation of these multi-cycle pulses. These are like pigeon-type pulses, right? That I'm going to talk to you how to generate them from ytterbium YAG thin disk lasers. Then we move on. This was actually very good in the beginning. Okay. Then we move on, and I tell you how to generate few cycle pulses, right? Femtosecond pulses from this type of lasers. And then I talk to you about how to generate sub-cycle pulses or light transient. These are the type of pulses that an eagle generates, right? And then if we are fast enough, then I talk to you about generation of attosecond pulses very briefly. And then tomorrow, then we talk about solar lasers, right? Because now you know very well what is the laser industry at the moment and why do we need a solar laser. So then how I designed the lecture, because I thought some of you might not have a background, right, in laser development. Then, so I start with terminology and basics, right, in case that you didn't have a laser lecture before. And then I talk to you about history. History is interesting, right, and how scientists work together to push a frontier. And then at the end, I talk about the recent development and experiments which are in the field. So let's just start with this. Maybe I just get my laser pointer. Then it's easier, I guess, to search. So now I have two hands, which is useful. Okay, so I would like to start with this picture. So this is a graph which is made by Gérard Moureau. So he's a laser scientist who got the Nobel Prize in 2018. And what you see in the graph, it shows that how the intensity of laser pulses changed over time. So these are years. So the laser is invented in 1960, and then we just follow this graph and how the development happened and where it goes, right? So let's start with 1960. That's the invention of the laser. What is a laser? In principle, you have some gain medium, laser material. Here you can see them in the form of rod, right? That's how the first lasers were. And then you need some mirrors to trap the light in a cavity, and you need to pump the medium, right? So this pump can be anything. You can pump the medium with electricity, with sun, or other lasers. And then what you need to put this stuff together. You need to put your gain medium there, then build your cavity. And one of your mirror, which is called output coupler, is a mirror that let the light to go out, right? That's why it's called output coupler. And that, when I say you have a 2% output coupler, means 2% of the light, which is resonating inside the cavity, can go out, right? Then you pump it. So you can pump it from the side, you can pump it from the end, right? It doesn't matter. So the pump light is not coupled to your cavity. And then the medium starts to lace, and then you get some output at the end. It has sometimes a delay. Okay, so let's look at the first laser which was invented. So the first laser which was demonstrated in history was a ruby laser. And here you can see the transition of the laser. Here is how the gain medium looked like, right? The scientist who developed it was Theodor Neumann. Actually, he developed it in the garage of his house. That's also very interesting, right? He wasn't at the university or with so many equipments. He developed it in his house. And the most exciting thing is that if by any chance you pass by Munich in Germany, there is an institute, Max Planck Institute of Quantum Optics. This is my previous workplace. And there you can see the real first laser. So it's in exhibition, and you can see the notebook of Theodor Neumann, right? So he developed it in the garage. You can see it in his hand. It was that small, right? And then how it's pumped, it's a 3-level system. So here you can see the atomic level of a ruby laser. And you just pump the laser, you use the energy to move the electrons from the ground state to the excited state, right, which is this blue line. Then the electrons relax and come to this excited state. And this is where you force them to lace, right? You put the cavity at the resonance at this frequency, and then the laser happens. So Theodor Neumann didn't get the Nobel Prize, unfortunately. I think this is also sad. But the Nobel Prize went to these 3 impressive scientists, Charles Towne, Basov, and Prokhorov. These were the people who did theory and predicted that lasing should happen at optical frequencies. The fun part is that the laser, the idea of the laser is not completely new. So people could do this kind of amplification at microwave frequency, right? And at that frequency, the whole thing was called maser. Okay, so this is the first laser, and then it's in 1960, and let's go back one more. Jared, maybe it's easier if you switch there. Can you go back? If I tell you next, and if you switch, maybe it's faster. So let's say. So then the thing that I want you to notice is that when you have a laser, you have a resonant transition. It means that the electrons are pumped from the ground state to another state. They are really pumped to a different state. So something is absorbed, right? So the pump photon absorbs, and you deposit energy in the medium. So now the energy is there. If you don't get it to lasing, it's going to heat up, right? Then the medium is going to get warm. So you want to get all the electrons in the excited state to a laser. Otherwise, things are becoming hot, right? OK, so, and if you go next, please. No? What's wrong with you? No, I think you have to go next. It just, I don't know what happened. If you go next slide, please. OK, so then this is 1960. And then in 1963, the first solar laser was invented, right? You see that the idea is not that new. And this is how it looked like. And if you go to this paper, you see that it's called maser, right? Because people still in the early days, they were calling laser maser, right? It's like at the microwave cavity. And it was a liquid laser. So they had the chromium atom in a liquid geometry, and they used scientists used sun to pump it. This was demonstrated, but people started to forget about solar lasers. Why? Because it was much easier and more efficient to use other lasers to pump the gain medium. So they started to build lasers to pump the other lasers and move to different frequencies. No? Aha. OK, we jumped, I guess. Or didn't we? OK, I think we jumped by accident on one slide, but OK. So now let's go back to our curve, right? So 1960 is the laser, 1963 is the first solar laser. And then people said, OK, these are like continuous wave. Now we want to generate pulses. Then they started to use different techniques to store the energy in laser pulses. And one of the breakthroughs that happened was with the mode locking of the laser. So that's when you don't use a chopper or mechanical thing to generate pulses, but the whole process is optical. And the mode locking also happened by chance in the lab. So the scientists and the students, actually, were working in the lab on titanium sapphire lasers, and then by chance they saw that it's locked, right? That they generate pulses. They talked to the supervisor. The supervisor was like, no, no, it's not possible. And then, but he came to the lab, and then said, oh, it is really locked. And they had a hard time to convince other people that they could optically lock a laser. So how the mode locking happens, or what is the mode locking process? This is one of the neatest process to just generate pulses from the laser. The whole thing is that you have many modes at different frequencies, right, at different wavelengths in your laser cavity, right? So these modes, they can be harmonics of each other, right? The fundamental, second harmonic, third. Now, if they are out of phase, like this, and so what you see at the output of the paper of the laser is the sum of these modes, right? Then they add up, and then you see these fluctuations, right? If you look at them in time, you see a CW beam coming out with the power. Now, if you find a mechanism to put these modes in phase, then when they add up in a superposition, then you start to generate pulses. But then the question, that's when you say, I locked the phase of my laser, right? Now I can generate short pulses. But the question is that these modes are randomly oscillating in your laser cavity. How to lock them? How to put them in phase, right? Did I jump in? Oh, I think there is something which is not showing up. OK, so then one of the techniques that was very successful in generating these mode lock lasers are the Kerr-Lenz mode locking. So if I want to explain you Kerr-Lenz mode locking, we have to know a little bit of nonlinear optics that I'm just going to go through, and then we go back to our mode locking process. So let's say that you have a light, you have a CW laser, or you have a lamp in the room, and you shine it to matter. So light is an electric field. What it does, it generates small dipoles, right, in your matter, and these dipoles emit, right? That's how the light propagates in matter, re-emit, let's say. If your light is not very strong, if you have a CW laser or a lamp, it's like a spring, right? Then you are in this linear regime, that whatever frequency the light has and shine to the matter, with exactly the same frequency, the light is going to be re-emitted and go through the matter. That's when you have the first order induced polarization in your matter, right? And we show it with P. Maybe you have seen it in your nonlinear optics lecture. So with this, you can also explain what is the origin of refractive index, right? Why different materials have different refractive index. Because it's just about all generation of this dipole, right? And how it reacts with matter. And also the thing is that there is a time delay in re-emission, right? It's not an instantaneous process. Now, let's say you have a very strong laser. Right now you have a pulse laser because you confine the energy in time. When you interact with matter, this dipole that you generate is going to be stronger, right? You can displace the electrons further away from each other, from their positive charge. Or instantaneous, oh, thank you. But you induce a polarization. That's why people call it virtual level. It means they say, oh, you excited the medium to the virtual level, and it's virtual because it doesn't exist in matter. You don't absorb, you just displace the charges, right, and induce a polarization. Now, the stronger the field, the laser, the bigger this dipole. So we talk a lot about this dipole today. And then for the attosecond pulse generation, the whole thing happened when the field was so strong that this dipole was not working like a spring anymore, right? People could not describe it. And then the new process happened. So then you can write this induced polarization with this Taylor series, right? Then it says that if your field is if the electric field of light is very weak, you induce the first order polarization. If it's stronger, you induce the second order polarization. And if it's very stronger, you induce the third order polarization. Then you've heard about, for example, this is when you generate second harmonic of the beam, of your laser beam. And this is when you generate the third harmonic of your laser beam. But it all intensity. So you need stronger light. So then we talk a little bit about these second order processes when we want to generate few cycle pulses. That's when I talk to you about optical parametric amplifiers or OPAs. But for mode locking, we are going to use this third order process, right? There are so many of them, right? We have solitone, Kerr effect, Raman, XPW, right? But what is needed for mode locking is this Kerr effect, right? Which is a third order process. Okay. Some interesting historical note. People invented the laser, that's 1960. Then at 1961, the laser, it was strong enough that they started to interact the intense light with matter, right? And then they could generate the second harmonic of the laser for the first time, right? It's like with the process that I just explained to you. And this is the original publication from Nicholas Bloomberger. He got the Nobel Prize in 1981 because of the demonstration of this kind of nonlinear processes and the work that he did in the field. And then you can see the input beam, at that time, they didn't have CCD cameras, right, to capture good pictures. So they have an input beam of the laser, and this is supposed to be the second harmonic, right? But you don't see anything here. And the fact is that the editor of the journal thought that it's a speck and it's a mistake. So when they wanted to publish the paper, he actually removed the second harmonic picture from the actual publication. So he's a very big guy in nonlinear optics. And let's go back to our mode lock laser. Now, you have your laser cavity, works in CW. You want to lock it, right, to generate pulses. So you need a process to put all these guys in phase. And what people used by accident was this Kerr effect. What is a Kerr effect? So the Kerr effect is a third-order process, and what it means that the refractive index of your material depends on the intensity of your pulse. So if your light is very intense, while it propagates through the material, the refractive index changes. See that now I have this N2 term, which is multiplied by the intensity of the laser. So now the more intense the laser, the more changes of the refractive index. So what happens to the beam if the refractive index of, if it changes the refractive index of the material while it propagates? Then you can see it here, right? Maybe you've already seen these things in your nonlinear optics lecture. So if you have a low intensity beam, you shine it to a piece of glass. It can be a piece of fused silicon. The light goes through. The Gaussian beam is a Gaussian beam. Now, let's crank the intensity of the laser pulse. When it propagates through the matter, the refractive index is changing, right, while it propagates. Then you start to self-focus the beam. So this is called the self-focusing process, and it's like that you have a lens here, right? Okay. So what a lens does in a linear optics, lens produces this phase delay, right? That's how the beam collapses together, the rays, and they collapse together and it's focused. So it's similar to a Kerr lensing or Kerr effect. So you have this phase delay on the x-axis because as it propagates, it gathers more of this phase, and then the light gets focused. So self-focusing is crucial for the mode locking. Okay, can you go to the next slide? Yeah, thank you. So this is what happens to the beam in space, right? The beam focuses itself. What happens to the beam in the time, right? Because now you have pulses, laser pulses. So the same thing happens in the time, right? If you look at the temporal profile, right, you have a short pulse going to the medium. And if you do the math and put the time, temporal response of the matter, then you see that there is a temporal lens, right, which is generated in matter, and then a process which is called self-phase modulation happens. Because of this nonlinear phase, you are going to chirp your pulse, means to, you see, you displace the different frequencies from each other. Your pulse becomes longer, and you generate new frequencies. Right? So this process, we also are going to use it a lot. It's called self-phase modulation. And it's because the pulse that you have is varying, right, in the time domain. Okay, so now let's use the Kerr effect process to mode lock our laser. So you have your gain medium, which in the case of the first mode locking was the titanium sapphire laser. You pump it from the side, and this is pumped with another laser, right, because it's easy and efficient. You have your cavity, so you have a high reflector and output coupler to let the beam out. Then you need two more elements. So you have short pulses, So you have to correct for the dispersion. Means that when the colors are separated from each other in the time domain, you want to put them back, right? So you need something to put them back in the time domain and make your pulse short. And you need a mechanism to do the mode locking. And the mechanism that's going to be used here is the Kerr effect. Okay, so how the whole thing works then? Now you turn on your laser. All these modes that I showed you in the cavity, they are excited, right? And they are resonating. If you have a chance to disturb this equilibrium, let's say, of the modes that they are just propagating in the cavity, then, because they are fluctuating, some of them have a small amplitude, some of them having a big amplitude, then if you have a chance to just excite one of them and trap one of them, then that one is going to get amplified, right? And then because if you trap one of these high intensity modes, that one is going to do a bit of self-focusing in the gain medium. It means that the beam is going to be a bit smaller. The divergence is going to be a bit less. So if somewhere you put an aperture, then you are just going to isolate this mode that by chance, you pushed it to laze in the cavity. And then after one round, if you have this hard aperture, the only mode that can survive is this one. The others, they all going to die out, right? And then the higher the intensity of the laser inside the cavity, this mode is going to be stronger and nicer and better. So then you need a Kerr medium, right, to do this self-focusing for you. And you can use the gain medium as the Kerr medium, right? Because if your laser is very intense, in the same crystal, the Kerr lensing can also happen. But then the question is that how to start it, right? How to excite this single mode, which is randomly oscillating in the cavity, and force it to win over all the other modes. Do you have any idea? Or if some of you worked with a femtosecond laser? It's very simple. That's why this thing was discovered by accident. So this is a random distribution, right? You need to produce a chaos in the cavity, okay? Because then there's a chaos, then one of them might win, right? And if the situation is in favor of that guy, then he's going to win over, right? How to generate the chaos? It's very simple. You knock on the optical table. Or if you have a fiber laser, you shake the fiber. That's how it was an accident, because the students, probably someone knocked on the table and then they saw, oh, the pulses are coming out, right? Then one of these high intensity mode wins over and then the laser is locked. So this Kerr lens mode locking was very important in the history of laser development. And also this gain medium, titanium sapphire, has been a very important gain medium. It enabled so many experiments in the lab. And you see it's very nice, right? You have a broad absorption at 500 nanometer. So you can absorb light at these wavelengths, and then you have a broad emission, right, from 600 nanometer to 1,000 nanometer. So, and then if you compress these colors and put them together, then you can generate femtosecond pulses. So here is a typical cavity of a titanium sapphire laser. And then you can see that here you have the gain medium, which is also the Kerr medium. Then you have your cavity, right? It's pumped, and you have something to correct for the dispersion. Here, people used to use prism compressors, right? But over time, the chirp mirrors were invented, which is also a very important technological development for generation of attosecond pulses in principle. So what is the problem with prism? It's glass, right? So if the intensity in the laser is very high, then you are also going to have Kerr effect and self-focusing in the prism. So you cannot scale the energy easily. Then people came with the idea of the chirp mirror. What is a chirp mirror? Is in principle a high reflector, right? And it has a very simple basic. So I have this video. Does it run? Yeah. So you have a chirp pulse, and then it goes to your mirror. Your mirror And then when it reflects back, it's compressed. All the colors are together. What is inside this magic mirror? You have layers of different coating, right? So the first layer reflects back, for example, the red color, and the last layer reflects back, for example, the blue color, right? So each color of light is reflected at different layer of the coating, and this way you just adjust for this timing, right? By the time of the reflection, and you can compress the pulses. What is good about what is bad about chirp mirrors is that it's very expensive, right? So because you need big machine to generate these optics. But what is good about it is that you can scale the energy of the laser pulses. So they were very important technologically. So titanium sapphire was cool, was beautiful, right? But then it also had another problem. You couldn't scale the energy and power of the lasers simultaneously. So people started to damage somehow the gain medium. So you couldn't just get, there's no free lunch, right? You couldn't just go higher and higher in energy and be happy. Then at one point, people started to work on ytterbium YAG lasers. What is good about the ytterbium YAG is a very nice material, right? So it has a high quality. You can use it as a very nice gain medium. But you see that you can pump it at these wavelengths from 900, let's say, to 950. It's not very broadband pumping. And it lasers at 1030 nanometer. You see that the emission is also very narrowband. So you cannot get femtosecond pulses from ytterbium YAG lasers, unlike the titanium sapphire. But you can get picosecond laser, and then maybe you find a way to make them shorter, right? So there has been 3 geometries of laser that people use ytterbium YAG. The beauty is that you can scale the energy and average power with this material, right? So people use it in fiber. There are ytterbium YAG fiber lasers, right? That you can scale the power but not energy. And then people used it in slab geometry. You see, it's like rod, but like a square type of rod, right? So these are called inoslab lasers, right? That the light is pumped back and forth, and then you can get very good energy and power from this type of lasers. And the other one is the thin disk lasers, ytterbium YAG thin disk lasers. So this is the technology that I was very active on, right? Before, last decade. So what is good about thin disk lasers, and what is the principle? So in a thin disk laser, your gain medium is very thin. It's a 200 micrometer thick medium. Okay, but you want to have it thick, right? Because that you have more matter to excite, right? But then it's very unconventional, so you keep it very thin. And then the gain medium is mounted on a diamond substrate, right? So diamond, because it has a very good thermal conductivity, it's the best. And then you have water from the backside that cools down. So you remember I told you that, okay, you excite all these electrons to the upper level. If you don't manage to bring them down to lasing, they are going to go to heat, right? So you have to remove this heat because just the temperature goes up and down. So then it gives you the possibility to do a very efficient cooling. And efficient cooling means that you can increase the power of the laser. I had a better one. So now the gain medium is so thin. How to compensate for that, right? Because then the output of the laser is going to be lower energy. Then what they put this gain medium in this kind of head, pump head they call it, right? And the idea is very simple. So if you have one pass, then you don't absorb so many pump photons. So let's let the pump to go in, and then let's have a geometry that forces the pump to go back to the gain medium over and over, right? So then you reuse the pump, and this way you can compensate for the thin gain medium that you have. Then how the gain medium is also working. So you have a high reflector coating at the backside of the crystal. So it's also like an end mirror of your cavity, right? So the light is going to come here, gets reflected, and go back to the cavity. Yeah, so now it's a very scalable concept, and you need this scalability because you want to generate higher and higher intense pulses, right? That's when you can study the new dynamic with light-matter interaction. So this efficient cooling led you to increase the average power. Average power is important, right? Because at the end, all your detector sees the average power. You want to be above the noise. And then, because the disk is also very thin, you can really scale the energy, right? You don't get a huge Kerr effect in the gain medium, and you won't damage the gain medium. This is how it looks like in the lab, right? So here you see this dot in the middle. That's where it's pumped. And then this is a real laser, the head of the real laser. Okay. So then with this new material, I mean, this is the work which was done by my colleague Oleg Pronin. For the first time, he showed this concept. And this is one of his lasers. So very simple. You see, you have the gain medium with the pump head, right? You pump everything from this side, and the pump that it's used is diode laser. So diodes are good because it's cheap, right? So price is important, right? So it's pumped by diode laser from the backside, goes to the head, reflected, and this is one of the elements in your cavity. Then you have the output coupler here, you have an end mirror here. Then the light goes back and forth, right? And then you get it out from. Then people showed, I mean, Oleg showed the Kerr lens mode locking in this kind of lasers, and then it's very simple. He placed a sapphire glass in the cavity, and you have a focus, right? So then you can start this Kerr lensing effect. And you have chirp mirrors to correct for the dispersion. So actually, 5 minutes. Yeah. Now I think I'm gonna, let me show you this too, and then we rest a bit. So this also shows you how this technology is scaled, right? You can have lasers in the bulk geometry, fiber, slab, thin disk. People could go high with the repetition rate, right? How fast the pulses are coming out, and also the pulse energy. And you see, if you want to increase the pulse energy, the repetition rate goes lower, right? Because it's just so much power, and it makes it difficult to run the laser. And then beside the ytterbium, people started to also study different materials which are similar to ytterbium YAG. And then you can see that you can get different pulse duration, right? From 1 picosecond down to hundreds of femtosecond, and up to 300 watts. Now we have a 1 kilowatt average power laser also. Okay, so what brings us, where we are now on this curve, we started with the invention of the laser. Now we mode locked our lasers, right? So we talked about oscillators. Now I stop here because you can see that there is a plateau. And that's where people kept damaging their gain medium, right? So they couldn't scale the intensity of the lasers further. And if you look at it, it's quite tough years. It's 1965 to 1990, right? So after this short break, then we start here. That's the concept of CPA, which got the Nobel Prize in 2018. And you see why it got the Nobel Prize, right? People were stuck, and no one could improve the performance of the lasers. Okay, so let's go for questions of any type. Historically, where you buy things, how much is it? Mm-hmm.
Thank you for the talk. The question is, do you have tunable or non-band lasers which are artificial?
Yeah.
And what are the wavelengths?
Okay. Okay. So this titanium sapphire laser technology that I'm talking about, especially after the break when we talk about CPA, these were the lasers that enabled the generation of the attosecond pulses. So for attosecond pulses, you cannot have a gain medium that gives you attosecond pulses. Why? Because all the material that we have in our surrounding, they absorb, right? They absorb below, the best case, below 150 nanometer, right? And the if you want to get a pulse which is that short, like attosecond, then you need to push the wavelengths to the XUV, right? So you can't get it from normal material, so you cannot put a gain medium and generate attosecond pulse. That was also one of the reasons that it got the Nobel Prize, right? It wasn't that simple. So the development of the attosecond pulses was so coupled to the chirp pulse amplification, or CPA, because that scaled the intensity, and then you could just interact with matter in a very nonlinear very nonlinear regime. So you could go beyond this ponderomotive regime that things are induced polarization. I mean, I think there is a lecture on attosecond physics, if I saw correctly, right? There is a lecture. So I just briefly mentioned at the end some basics, and I'm sure that in the lecture it's going to be covered very truly. Then you generate them in principle in the interaction, with the gas, right? In a non-ponderomotive regime. But you cannot build a laser, right? So it's just a nonlinear process that you use. Yeah, I couldn't hear it. I can also repeat the question.
Now, I think it is now.
Perfect.
Okay.
Yeah.
I believe probably in your lab you are generating the femtosecond pulses using the Kerr lens medium. I just thought of asking, we can also use saturable absorbers.
Yeah.
Why do you prefer the Kerr lens instead of the saturable absorbers?
Yeah. So the magic thing about Kerr lensing, Kerr lens mode locking, let's say, it was the bandwidth. So there were many other techniques, right? People were using mechanical, acoustic techniques, and so on. Saturable absorber is one of them. But they have a narrow bandwidth. So you can get nanosecond, or with a saturable absorber, you can get picosecond or hundreds of femtosecond pulses, right? But the Kerr lensing the bandwidth is huge, right? You can get out of it. It supports a bandwidth of sub 10 femtosecond pulse, right? From titanium sapphire laser oscillators, you can get 5 femtosecond lasers, 5 femtosecond pulses. So that's why it influenced a lot, somehow, the laser technology.
Thank you. Another question from the audience?
So thank you very much for the nice presentation. I tend to divert a little bit, and I just want to ask you, because you have generated isolated attosecond passes, I hope so. And one of the challenges of isolated attosecond passes in terms of the application is harmonic efficiency, and because of the low harmonic efficiency of the spectrum that we are generating, that's making it not possible to generate isolated attosecond passes with a time duration of less than 24 attoseconds, which we assume that's the period that electrons do vibrate within matter. So I don't know which technique you are adapting to ensure that harmonic efficiency is increased.
Mm-hmm. So that's actually a very good question, and that's the bottleneck of the current attosecond technology, right? Because you use these very short pulses that, I haven't shown them yet, that comes after the CPA invention, but you use these high energy pulses, right? And what you do, so let's say you have a 5 femtosecond pulse, then you have 2 oscillations below the envelope of your pulse, right? And then you generate, you kick the electrons at one part of this field and then recombine it back, right? So you are interacting with gas, which is not a dense medium. Then it means that the amount of photons that they are emitted is very low. And then the higher harmonics that you go, right, then this efficiency drops, right? Because you just simply, I mean, I talk about it, I think. In the next session, maybe I move faster to reach this attosecond pulse. Because then simply you just kick the electron further away from the atom. Then the probability that it, in its journey back to the atom, it really smashes the atom drops, right? So then the efficiency becomes lower and lower. And this is a drawback now at the moment. So it's, people worked a lot on phase matching techniques in the gas to increase the efficiency. But the efficiency is not enough to do, for example, XUV pump, XUV probe kind of spectroscopy, right? You always, you can't, it's not, you don't have enough photons in principle. But, right, with the isolated attosecond pulses, I mean, I have a very good graph that I show after the break, that the whole thing is that only the highest photon energies that you generate in this process is isolated. It means that you don't have a pulse train, you have one pulse, right? And that's simply because it only comes from the contribution of the highest amplitude of your field, and you have just one peak, right? The others, they come from many oscillations, right? But saying that, I mean, it's beautiful. That's what actually Ferenc got the Nobel Prize for, that he could measure these isolated attosecond pulses. But people do many research with this train of attosecond pulses, and there are techniques to measure them. They do polarization, gating, rabbit, and so on. That's actually the Nobel Prize, the contribution of the other two Nobel Prize winners for the attosecond, Andouille and Pierre Agostini. So, yeah, maybe the next generation want to improve the efficiency of attosecond pulse generation, right? So we need a new idea. And people do now, I don't know, in SLAC, people try to get these short pulses from electrons, which is very promising, right? And with these undulators, they try to seed it to get one single pulse and so on. But at the moment, it's somehow the limit, right? We hit the limit in terms of efficiency. And it's not very efficient. Right? Questions? It can be also basic questions, right?
So there is no questions online, so
okay.
you can continue now.
There's one more question there that I can take. Let me see what's there.
Good morning.
Good morning.
Okay, in my laboratory at the Kenya Bureau of Standards, we realized the SI unit of time using the cesium resonance frequency, cesium atoms. So we've been advised by the scientists worldwide that now we are moving to optical clocks. From cesium, we are moving to optical clocks.
Yeah.
So maybe you can comment on what optical clocks will enable us to realize the SI unit of time.
So then I think for that one, actually maybe it's a very good topic for the next summer school. So then you need to go to the realm of the frequency comps, right? So this is the, yeah, you can go to optical frequencies, right? And this is, I think, that's why the Nobel Prize was given to the frequency comp. This is the Nobel Prize by Ted Hensch in 2005, was it, right? I think in around 2005. And you can just have, you can clock everything with the frequency comp. So the thing with the frequency comp is that it was also one of the enabling technology for attosecond pulse generation. So I just bring all these Nobel Prizes to just show you how they are coupled, right? Because, I mean, I have a slide, I think, after this, that when you have a short pulse, then you have, there is a new parameter which shows up, and it's called carrier envelope phase. And the contribution of Professor Hensch was to stabilize this carrier envelope phase that I'm going to show in a bit. And with that, then you have a precision to measure at optical frequencies. Right, and then the other, so back to the isolated attosecond pulse generation, this CP stability was the requirement to generate isolated attosecond pulses. So you see that first the laser had to become strong, then the phase under the envelope that I'm going to show had to be stabilized, right? Then another Nobel Prize. And then these technologies were put together to generate the isolated attosecond pulses. Just show how much we have to work together, right, to push the frontiers of science. Micrometer, 200 nanometer. Mhm.
Would the thickness of this disk affect the diameter of the field distribution?
Yeah. So actually, very good question. So this is actually relevant to the solar laser. Let me see if I can go back fast to a slide. Oh, now it's fast. Okay. Do I have a, yeah, here. Oh, I passed by. Here. Okay. So you define something which is called cavity mode. What is the meaning of cavity mode? Means that, okay, this is a thin disk, and then this spot in the middle is the size of the pump, right? Then you design your resonator that the beam which is propagating inside the cavity, this laser beam, has almost the same size as your pump, right? Because you want them to overlap to get the energy. Now, what happens if, okay, so you can say I have the heat problem, as you mentioned, right? I make it thin. So what about making this pump beam big, because then I have more atoms in this area, right? And make the cavity beam, cavity mode also bigger, right? Then this way I win, right? But then that's also come with a price. So when you increase the cavity mode, the lasing threshold goes higher. So you need to put more pump to bring the laser to acting, right? Then they say that there is no free lunch, then you really feel it, because we are working on a type of solar pump thin disk laser, and then we really wanted to push this frontier of the limit of the cavity mode to the edge, right? That we use as much, because it's so hard to focus the solar pump very well, right? So we thought, okay, we increase the cavity mode. But then your laser threshold just goes higher and higher. Yeah. So then you are trapped in a limit somehow. Right? So most of the time, I think the cavity modes are around like 5-6 millimeter, right? Your pump spot is also like around that range.
We have a question here.
Mm-hmm.
Why are laser pulse dynamics observed in the time domain?
Oh, okay. So let's go back. So I think the question is on cell phase modulation, isn't it? I guess. This one, right? Okay. So let's go back to space first, because the space is easy to understand. The whole thing that we see the self-focusing is because you have a Gaussian beam, right? When you have a Gaussian beam, means this part, you see that it has the highest energy, right? And the wings, they have lower energy, right? So when these pulse propagate into this glass, the center part has a higher intensity. It means that it sees higher changes of refractive index, right? And then the wings, they experience lower changes of the refractive index, simply because everything is intensity dependent. That's why you have this lensing effect. Now, if you look at the pulse, right, a short pulse, you need a short pulse to see the Kerr effect. Then you see it has the same distribution in the time, right? So you have the highest energy here at the center, and the wings, they have low energy. Right? So then this part of the pulse in the time domain experiences a higher nonlinear phase shift. It's intensity dependent. And then due to this nonlinear phase shift in the center, you start to generate new frequencies. See that in the time domain, in the center part, temporal center part, you have more phase shift, and then you just generate these two wings of new frequencies. So they are counterpart of each other, one in the space and time domain, and the whole thing is that you have a nonlinear phase now that changes and modifies your pulse while propagating in the medium. Yes?
You briefly mentioned something on the application of these ultra-short pulses on lightning control and remote sensing.
Oh, and remote. So the question is that what is the application of these short pulses on control and remote sensing? So this is also a big field, right? I mean, femtosecond pulses are used for many applications. I mean, in case of the control, I can give you an example. Maybe you want to look up the work afterwards. I mean, it's also like a hype research at the moment. That if you have a very short pulse, this is not very short, but you have like 2 oscillations of the electric field. Let's say you have a 5 femtosecond pulse. Then, and if you inject it to shine it to a matter, then there are several groups who work on it. You can steer the electrons in the solid, right? So you can oscillate the electrons back and forth, right? So if you move the electrons really back and forth, what does it mean? It means that you have a current. So then you have a light-induced current, which is controllable. So this is, for example, one of the examples that you can have in terms of control. You can do a lot of spectroscopy, imaging, femtosecond spectroscopy, femtosecond imaging, and then also you can do a lot in monitoring, right? So if you would like to, well, I have a talk on that, but I think it won't fit now to our 4 hours lecture. But for example, if you would like to identify different molecules, right, then there is something which is associated to molecules which is called fingerprint. Like each of us have a specific fingerprint. Each, let's say, chemical bond has also specific absorption frequency. Then you need a broadband pulse and short to detect all these, let's say, molecules in the atmosphere or something. And I think one of the winning technologies in that case are these dual frequency comms. So the frequency comm was also very influential in that kind of research.
Now we stop question there, we continue.
Okay. So then what I do, because I see so much interest on the attosecond pulse, I maybe, okay, let's go back. So I try to, I mean, I skip some details for the OPA to just reach the attosecond pulse. Oh, we have also tomorrow, right? Okay, so we have 2 hours tomorrow. Okay, so where were we? We were here, right? Scientists are stuck. No one can increase the intensity of the laser pulses anymore. They just damage the material inside, because inside the cavity of the oscillator, you just have so much energy, right? It damages the material itself. Here comes the next Nobel Prize winner of 2018. This is the idea which was developed by Gerard Mouot and his student Donna Strickland. So she was a PhD student who worked on it. This is also an indication for you guys, right? That when you work on a project as a PhD, there is a very high chance when you have a seminal contribution to get recognized. And this paper is like a 2-author paper, right? So it's just these 2 people contributed. At that time, so this happened in 1985 in the University of Rochester in the US. And what was their idea? This idea is also simple, and it's not new again, right? That's why we should learn about the history. This idea has been demonstrated at microwave with masers, right? And what Gerard did, he just implemented this idea at the optical frequencies. So it's good to know how things developed in principle. So what Gerard thought, he thought that, okay, we are damaging the laser gain medium because the intensity is so high. How the intensity is calculated, it's the energy of your pulse divided by the area of your pulse by the temporal duration. So it means the shorter the pulse, the higher the intensity. Then he thought, okay, I want to have high energy. So this is the parameter that I want to scale. So the area is also, we just talked, it's limited, right? You cannot increase the cavity mode forever. Then the laser threshold goes higher and you cannot even laser. Then he thought, okay, I will play with the time. This is the 5 femtosecond pulse, which is propagating inside the titanium sapphire laser cavity, let's say. He thought, okay, what about stretching it in the time domain? Means to just chirp it. We saw the chirping, right? To just have different frequencies coming at different time right? Like a rainbow of colors. And then I send it to a laser gain medium to amplify the energy. Because now the pulse is long, I won't damage it. And then I will use some techniques to compress it and put it back together, like the chirp mirrors did, right? So this is called chirped pulse amplification, or CPA. And that really changed the history, right? You chirp the pulse, amplify, and then you can scale the energy. So maybe you just go to YouTube and have a look on one of the talks by Donna Strickland, because she talks a lot about how this happened. The experiment was also very funny because she had a very long fiber. The fiber was really bad quality, you know. Some part of it, chance really helped her, right? It's a very motivating lecture to listen to. And it's, I think, available, many of them, in YouTube if you want to watch. So then what people did, now we talked about these titanium sapphire oscillators. Then they put the oscillator here. You see, it's another laser is used to pump it, right? So the oscillator is here. Then they stretch it. There's a stretcher that it stretches the pulse to nanoseconds somehow. And then they send it to a titanium sapphire amplifier. So you again have the gain medium. The laser pulses go there, back and forth, amplify, right? And then at the end, they use grating compressors or chirp mirrors to compress these pulses. This has been a game changer because people could generate 25 joules of energy, right? And they could go up to 1 hertz rep rate, and the pulses are almost, you can go down to 20 femtosecond pulses. And now it also goes really crazy. For example, this French company, Thales, I mean, you can buy, not us because it's very expensive, but organizations, let's say, they can buy this petawatt system. So it's extremely intense laser pulses with so much energy. So I mean, it's even commercially available. Okay, then people started to put this concept also on ytterbium YAG lasers. Again, the same concept, with the difference that now here you can scale the power. So you have an ytterbium YAG oscillator. You stretch it in a grating stretcher in this case. Then you send it to an amplifier. Then you have again thin disk here to amplify the pulses. And then you send it to a grating compressors to put the colors back and generate short pulses. How far they could go? You can get 200 millijoule 1 kilowatt pulses. These are huge energies. I'll show you an example very soon. But the pulses are pretty long, right? They are picosecond. That's because the emission cross-section of ytterbium YAG is very narrow. Okay. Then the question was how to get these pulses shorter, right? So now you have energy, power, and everything. It's a beautiful technology, but it's a bit long. Then people thought, okay, there is this phenomena which we talked about, right? The cell-phase modulation that used for Kerr-Lenz mode locking. So they thought, okay, let's use the same phenomena, because in this, when you have a Kerr-Lenz focusing, let's say, you also generate new frequencies. And if you can generate new frequencies, when you compress it, you have a shorter pulse. Okay, I skipped this one, right. But then there is a problem. Maybe first we look at this. There is a bit of problem with this Kerr-Lenzing. We just talked, right, that the Gaussian beam has a different intensity distribution. Now, I have my laser pulses, and I just want to put a glass out of the cavity, right? So these are now I'm coming out of the laser cavity. I put a piece of glass, and I focus the light into the piece of glass. So then I have cell-phase modulation. I generate new frequencies. But if I look at the beam in space, we talked about it, that's what happens specifically in the lasers, right? Then at different wavelengths, the beam size is changing, right? So you don't get a homogeneous beam. It's good, but not perfect to get a perfect short pulses. That's when people started to develop the idea of Herriot cell. This is also a very hot topic at the moment. I think if you look at the optics letters, there's like 10 papers per month on Herriot cell spectral broadening, because it's also a scalable technique. How the Herriot cell works, they figured out that if they do this, if they inject the nonlinear phase to the matter in small amounts, they can, and put it in a cavity, they can have a very good spatial quality, right? The beam is going to be good because these higher order modes are going to diffract out in the cavity. So what is the concept of a Herriot cell? Then I have this video for you. Then in principle, you need 2 mirrors to trap the light. And you have a focus in the middle, right? And the light just goes back and forth. And you put your gain medium, which is very thin now, at the focus. And at each pass of light, you add a very small phase shift, nonlinear phase shift to the matter. Then you slowly do the spectral broadening, and if there is any inhomogeneity in space, that's going to diffract out in the cavity. So we just talked that you also need something to compress the pulses. And what people do very cleverly, here they have 2 chirp mirrors, right? So the light passes through, gets a bit chirped. Here it gets compressed. New frequencies, chirped, compressed, new frequency, yeah? Then you go back and forth, and you can generate very short pulses, right? So this is how it looks like from side view. And you have 1 mirror, you see, and the light just hits at different points to the mirror. And this is how it looks like in the lab. You start with a ytterbium YAG laser. You cannot see it by eye, right? Because it's at 1030 nanometer. And then you get so much spectral broadening that then you start to see the laser dots on the mirror. How the spectrum looks like? You start with the orange spectrum, and you can broaden very nicely to the blue one. And this is a very typical textbook, cell phase modulation, very beautifully adding new frequencies. Okay, maybe I skip this one for the sake of time. Well, okay, so now people can use CPA, scale energy, scale average power, and get short pulses, like 20 femtosecond pulses. Let's go back to this graph and look a little bit, right? So this is invented in 1989, I guess, right, the CPA. And then, is it 2001? So the attosecond pulses are demonstrated at 2001, which is around here, right? So you see that then the CPA just was very established, and people could do very intense pulses. But what kind of physics you can see, right? I just tell you, okay, let's increase the energy of the pulses and intensity. We can see better and better. Now people at the moment, you do high harmonic generation it showed up in the discussion. And this is where you can look at the dynamic of the bound electrons to your atom, right? That's their time scale. They move that fast at the attosecond time scale. And if you really scale the energy, you can start to look at the relativistic optics. We don't have facilities there yet, right, operational, but there are these ELI beam lines. So this is a big laser facility in Europe that it's like a big infrastructure, big building that people try to build these very big lasers based on chirp pulse amplification to be able to study this kind of dynamics. So, and if you look at this curve, you see this is what Gerard extrapolated, right? That we should reach there, which is very important because then you can look at the nonlinear quantum electron dynamic. But if you look at the curve, you see that it's rolling off, right? So probably it doesn't reach this kind of intensities, I mean the CPA technology. By the way, okay, it's very generously extended now at the moment to that point. So you see that then again, a new kind of technology is needed to boost the energy of the pulses. Okay. So how far we can go, right? So that was also the question, if we can have an attosecond laser. We are not, it's nice, right? But we are also very limited. For example, if you look at the gain media that we have, so you can have at around 10 micrometer, you can have gas lasers like CO2. Then we have ND YAG, ytterbium YAG, erbium at this range. Then you have dye lasers, ruby, let's say, and some argon laser, excimer laser down to here, right? And here is where we hit the absorption. So matter starts to absorb. It means that we cannot have any laser below this kind of wavelength, so we have to find a different way. Then the other thing is that you do cell phase modulation and everything, but again, the pulse duration is short, right? You are at 20 femtosecond. You want to make them shorter, right? Shorter and shorter. How to do it? So if you look at this laser diagram, right, it talks about the first generation of femtosecond pulses, which was dye lasers, and the second generation, which was ytterbium YAG, titanium sapphire lasers. And you can scale their average power or energy, right? But you cannot go diagonal. And then there was the emergence of the third generation femtosecond technology. This is the technology based on ytterbium YAG lasers. But you just saw that they give you 1 picosecond pulses. And the question is how to make them shorter, right? If you want to make them shorter, then you need to generate bandwidth, right? You need more frequencies to put together in the time. And you want to amplify. So you can do it by doing supercontinuum generation and so on, but you want to amplify them and make them energetic. A concept which is coupled now to this to ytterbium YAG lasers is the optical parametric amplification. This also is a Pondermotive effect, right? It's the second order nonlinearity that we talked about, that you just can send an intense pulse to a crystal and induce a nonlinear polarization. And then you can transfer the energy. This second order nonlinear process helps you to do the energy transfer. How does it work? Then let's say you have a pump laser, which is very strong but long, like a ytterbium YAG laser. So you can have joules of energy there, but it's 1 picosecond. And you have a low energy laser, but very broadband. So you have a titanium sapphire laser, which gives you 5 femtosecond pulses, but with very low energy. Then you can focus them in a nonlinear medium, provided that you have the phase matching and everything. We talk about it a little bit. And this way, you can transfer the energy from the pump to the signal, make the signal amplify, and then because of the conservation of energy, you generate new photons, which are called idler. So if you look at this diagram, then you see that I'm at the virtual level, so there is no absorption. It's an instantaneous process. I pump my material to a virtual level, induce a nonlinear polarization, and then each of these pump photons can break to a signal and idler, right? And then I just transfer the energy from the pump to the signal, and I can make my signal stronger and stronger. So this has been a very good technique for many years. And some of these big facilities that I talked about, they are using now OPA. Okay, So what you need to have when you do OPA is something which is called phase matching. What is the meaning of phase matching? Maybe I go one back. So for this process to happen, you need to have a high energy photons, right? The energy of the photons should be higher than the energy of the signal. Otherwise, they cannot give away their energy, right? And higher energy photon means higher frequency, right? So then there's always the frequency of your photon is higher than the signal and higher than the idler. But if you know that if you have light at different frequencies, because of the refractive index of materia, they have different speed, right? That's why they get chirp and disperse. So you have to somehow compensate for this speed, that they see each other, right? Otherwise, they walk away from each other very fast, temporarily. So the phase matching process is the process that makes sure that these three interacting pulses, can propagate in the gain medium at the same speed, right? That then this exchange of energy can take place. And you can write down, so simply it's the conservation of momentum, right? Then you can do the formula, right? Oh, okay, what happened here? Okay, so you can do a bit of formula. I think you get my slides afterwards. You can look at the math, and you can fix them together. So how to do the phase matching, right? How to force these pulses to propagate in the gain medium together. There are different ways. One type is called degenerate OPA, right? And this is just to use the nature. So what the nature offers us, if you look at the refractive index changes over the wavelengths in material, right? Then you see that there are some points that they are called zero dispersion, right? Or saddle points. So everything is chirped. In this direction here, everything is chirped. In the other direction here, right? Normal dispersion, anomalous. But then in between, you have these saddle points that the dispersion doesn't change that much. The refractive index doesn't change that much. So then scientists thought, okay, let's use this zero dispersion point. It means that the dispersion for light at these frequencies are almost the same, right? So then they propagate with the same speed. That's one of the ways to do it. But then you have to have your system at these specific wavelengths, right? That the nature offers you. The other trick is to phase match, use the geometry, right? To phase match with geometry. How does it work? So if this is your signal and this is your idler, they walk away from each other. When they propagate, they walk away from each other. Now, what about giving an angle input that just put the two beams like in an angle, non-collinear angle? And the idler goes faster, let's give it a bit more angle, right? That when it reaches there, they see each other, right? So to just play with the geometry. These are also called NOPA, or non-collinear OPA, and you can phase match very nicely. A very broadband signal. And you can see, for example, this is your pump, and the seed comes in an angle, gets amplified, and then you generate this idler at a rainbow of frequencies spread in space. So this is the trick, to put the signal and idler, at the same speed, but you also have to phase match the pump. And for that, you use by a nonlinear crystal, the type that have two refractive indexes at two different polarization, right? Uniaxial crystal or biaxial crystal. Maybe you've heard about the BBO, for example, a very famous one. It means that the crystal has a different refractive index depending on the polarization of the light, right? Then you just put the pump on one axis, the signal on the other, and then they can walk together. Okay, so you need to think about the phase matching, right, if you want to do the OPA. Now, you want to build an OPA at home, right? what do you need? You need a broadband seed pulse, right? You want to amplify these 5 femtosecond pulses. You need a high energy pump pulse. You can have an ytterbium YAG laser, right, which gives you picosecond pulses, but with very high energy. And you have to make sure that this pump and seed, they see each other in the time domain, right, because things jitter, right, and move. So you need a kind of synchronization in time that they stay together. And then people, you see that because the seed pulses are very short, people tend to stretch the seed pulses to the duration of the pump. This way you can extract more energy, right? Because they see each other better in the time domain. And then they started to use the term OPCPA, which is OPA plus CPA, right? So then it's very similar to this chair pulse amplification with the difference that now you can generate very short pulses with high energy. Then again, you stretch the seed, you amplify it in an OPA process, and then you compress it afterwards. Okay. Yeah. And then you put your seed pulses, your pump laser, you synchronize them, that the pulses go together, and you send them in a nonlinear crystal, right? For example, this is a NOPA, and you get the amplification. Then I talked about this ELI project. This is also a very big infrastructure. You can see, I mean, I think they have like 3 locations in 3 different countries, but the one in Czech Republic is dedicated to high energy femtosecond pulses and attosecond pulses. And you can see that they are aiming at generation of huge energy, right? I mean, 2 joule petawatt lasers and so on. So this building actually is existing at the moment. And if you happen to be in Czech, it's a very good place to go for a visit and see how. And then it also works based on a beamline. So in Hungary, there is an attosecond one, is another one, yeah. And Romania, I think the 3rd satellite is Romania, right? Romania, I think it's on the nuclear science board. Yeah. The Hungarian facility is also, I think, in operation. Yeah, the building is there, the lasers are there. And then you can also ask for beam time, right? You just submit a proposal, you can go there and do the experiment. They are very open to, I mean, it's a facility, right? Open to everyone. Yeah. So you see that it's like short pulses, not that short still, 20 femtoseconds. But they, for example, they use here in the 2nd beamline, they use ytterbium YAG lasers to pump OPCPA, ytterbium YAG thin disk lasers. The other one is built by this LLNL in the US, and these are titanium sapphire technology. One thing that maybe is interesting for you, you see that this L4 beamline, it gives you 130 femtosecond pulses at 1 shot per minute. So you get 1. Okay, good. So now let's just make the pulses shorter and shorter, right? Now you have OPCPA, you can go below 20 femtosecond pulses. So what happens when you make the pulses shorter and shorter, right? I was talking about these eagle type pulses, right? That there were like 1, 2 oscillations. When the pulses are very short, you are at sub 10 femtosecond, then you have 1 or 2 oscillations of the electric field, right? This is called envelope in laser, I don't know, language. And if you want to calculate the intensity of a pulse, this is the envelope to the power of 2, right? This is what you see on your monitor, right? You never see these oscillations because we don't have a detector that is fast to show us these oscillations, right? But they exist. But you need to do attosecond streaking to see them. Okay, so if you want to make a pulse short, you have to make the spectrum broad, right? You see they have an inverse relation. The broader the bandwidth or the spectrum, the more color you have in frequency, it gives you a shorter pulses in the Fourier domain, if you Fourier transform it. So you have to generate colors and put them together in the time domain with a chirp mirror or something to generate these pulses. Now, when the pulses are very short, you have 1, 2 oscillations of the electric field. There is a new parameter that now it's important, and that's the carrier to envelope phase. Carrier refers to the electric field, envelope is this guy, and it matters that what is the position of the highest amplitude of your electric field relative to the highest point of your envelope. So this is called carrier envelope phase. And if you have a laser, shot to shot, pulse to pulse, this phase moves randomly. So it's not like that every pulse has exactly the same relation. It moves around, right? Because simply there is dispersion in your cavity, the group velocity and phase velocity changing and so on. So if you can fix this under the envelope, that at each shot of the laser, you always have this electric field exactly at one position on the envelope, under the envelope, then you can have an optical clock. That's what we discussed, right? You have a precision, right? You have an optical precision then for your measurements. And you can use it as a ruler then, right? So one more thing that maybe it makes it easier to grasp. When this guy moves, this phase, this whole spectrum, you see it's like a ruler, right? This whole spectrum moves back and forth a bit, right? And if you fix this phase, this ruler is going to be exactly at the same position all the time. That gives you this metrology, a frequency comb, that's what they are called, and it's like a ruler that it's the most precise ruler in the world at the moment. Okay, I have a video. So let me see if it runs. Do you run? Oh, it was too fast. I think you can run my video, right? I mean, there is a, there should be a, here there should be a bar that you can click. Does it show up? Or maybe it doesn't show, okay. So in principle, it shows you how the whole thing moves, but why don't you run? With these videos, they never, okay, now I can move it. Okay, so, now I'm stuck. Okay, so to stabilize this phase, if you stabilize it, then people say that you have a CEP stable laser. I mean, that is super precise. And this is what you need in principle to generate isolated attosecond pulses. This got a Nobel Prize in 2005, as I mentioned, by Ted Hensch and some other Nobel laureate. And their contribution was just to play some tricks that the electric field stays at every shot of the laser at the same place. Okay, let's go back to our curve. Now, we just talked about OPCPA lasers, OPCPA technique. But this is also limited in terms of the bandwidth and pulse duration. You cannot really go shorter than 5 femtosecond pulses. And then you see that also at these very short pulses, the CEP becomes important. Then the question is how to make the pulses even shorter and even stronger, right? And why do you need that, right? Where do you want to shoot these exotic pulses to? Okay. So then I talk now about two, let's say, way to make even shorter pulses, not attosecond yet, I mean almost attosecond, and how to scale them even to higher energy. So I start with this one, with the NIF. This is the National Ignition Facility in the US. Maybe you've seen in the news, I think they had a breakthrough like several months ago that they could successfully shoot to their sample with the high energy lasers, and then they could just generate like sustainable kind of energy. But what they have, this is the actual picture, they have a laser which is as big as a football field, right? So, and then they just combine the energy of these individual lasers together, and they focus it on a target. And what they look for, they are trying to do fusion. I mean, what happens in sun, they try to do it on the planet Earth to generate energy, right? And they had a very successful, I think, experiment, like several months, it was all over news, right? That they could successfully show that this can happen with laser. So these are really powerful laser, exotic one. And then the other ones which led you to go below 5 femtosecond and even shorter pulses that OPCPA can give you are the optical waveform synthesizers. So how does it work? Let me see how far, okay, we are 10. So how does it work? It's also a very beautiful concept, right? That let's say you have a very broadband pulse that none of your techniques for compression and stuff, they can't work with it because it's just the bandwidth is huge. You have a super continuum. Then what you do, in principle, you separate the colors, right, in 3 different channels, and then you compress each of them and put together and can generate very short pulses. So let's talk about it more. Okay. But what you need to generate these pulses, which are super short, like eagle-type pulses, you need a very broadband spectrum, like a supercontinuum, and you need carrier envelope phase stability, right? This is the one that we just talked about. Okay, so then I just show you this video, which is very nice. This is the work which is done by Lefterius. The first guy who showed it is Lefterius Goulioumakis. And you see that he generated this very broadband spectrum, right, with very high energy, millijoule energy. Then he used some beam splitters to split the spectrum to 4 parts, right? And if the video, oh, good. So this is actually the actual device. This is a picture of his device. It's so beautiful, right? So that the light is so broadband that it's white, right? It's a white light. Then it's sent to this synthesizer. Each channel supports part of the spectrum. And if you calculate the Fourier transform of each of these spectral portions, they all give you like 5 femtosecond pulses already, right? It's like you have 5 femtosecond pulse here, 6 here, you know, it's just all short pulses, right? So then you send them to these channels, and then in these channels you also have chirp mirrors to compress them. And then in each channel you have a translation stage that you can change the delay between these arms. I don't know if you've seen these sound synthesizers that people in music use. That's exactly the same thing, just with light, right? Oh, this also have to. Okay, why the video does, okay. Do you have any chance to run this video? That's a good video. Oh, no. No, right? It doesn't work? Right, this one, this button. That's the one that I can't reach. Right, so you see that the beam comes in, it's splitted to 4 channels, and then it's recombined, right? And then you can generate these light transients. Now, if you move the delay of these arms, you can shape the electric field of your light. Very nice. And you can generate non-sinusoidal shapes. You see that the electric field was sinusoidal, you can do the non-sinusoidal. So this was cool. And they showed, these are called optical attosecond pulses, right? Because you are still at optical frequencies, right? You are still using solid and matter. If you synthesize these pulses, then you can get 380 attosecond pulses. See, you are very short now. And I think with this, okay. So now, so I leave the attosecond pulse generation for tomorrow, but before closing this session, just to give you some numbers, right? When are we happy, right? When a short pulse is short enough for us, right? Or why do you want to make things shorter and shorter? So now we have the optical attosecond pulses, right, that they are below 1 femtosecond. So you can say that, okay, short pulses are needed. Oh, you have to run this video. This is my favorite video. You can say that we need these pulses to save the world. Okay. Let's see. Oh, nice. Yeah, you need short pulse. You need to be fast, right? This is one reason. Yeah. Well, it worked, right? Or you say that, oh, I need even shorter pulses because there are some phenomena that they are happening and they are very fast. So I need a fast camera to capture them. And these kind of phenomena are electron dynamics in the atom. They have the attosecond time scale. So you need even to go shorter than 1 femtosecond, right, to be able to see and visualize these kind of processes. So then with this exactly, so I just end the lecture today, and then tomorrow we talk about attosecond pulses and solar lasers. Now if you have questions.
We can thank the speaker first. Any question? So no question. Maybe Prof, you have something?
Not really, but just to appreciate Fatahi for the well-prepared presentation. I was just seated with my students here, and I was asking, are you familiar with that? And they were excited to say, yeah, yeah. So I think that is quite good. Just to mention that one of our staff is actively involved in attosecond pulse generation, the one who asked a question. Just in the course of your lecture, somebody asked a question. Probably, yes, so we are also doing some research in that direction. We have a student at master's level. So probably in the course of this summer school, you might, he might also connect with you and see probably how far we can be able to interact on this matter. Exactly, yeah. Mm-hmm. Okay, thank you. We look forward for tomorrow, the solar laser. Thank you.
intense, they were short, and they had very well-tuned oscillations. I repeat it again. Okay, I see it, yeah. So maybe I can also go back to some slides. Yeah, first. Where were I? This is like here, I guess I have something right. Yeah. So I think the best way to understand it is based on this model, right? Put it up. So if you have a ball which is attached to a spring, right? Now let's say with your hand, you just put a force on this ball and move the ball, right? And then release it, right? In, let's say, oscillatory manner. Then each time that you pull the ball and release it, then the spring is gonna oscillate. And if the amount of displacement or the amount that you pull the ball back is not so far away, then you will follow a linear path, right? You pull it, then it's gonna oscillate at a frequency which you can explain by a linear relation. The Hooke law, right? So this is exactly like this. So the spring is, let's say, is your matter, and the ball are the electrons, let's say, or the charges that they are in the crystal, right? And they are just sitting there around the atom. Now, let's say that you are very strong, right? And then you pull the ball really hard, right? When you release it, then you somehow destroyed this hook, this spring, right? It just doesn't oscillate very nicely anymore. So then it's gonna be nonlinear behavior, right? You are out of this nonlinear regime, and then you cannot just say, oh, the force is scaling with the, I don't know, the frequency of the spring is scaling with the force. So this is exactly the same in the matter. When you shine the light, I mean, light is a force, right? You have energy. When you shine the light to the matter, this force, which is going up and down, starts to jiggle the electrons in the matter, right? And then starts to make these dipoles, right? Sometimes the negative, they are a bit pushed up, they are a bit pushed down. And when the light is very weak, then everything is scaling in the linear regime like this one, and nothing happens, right? The light goes in, the light comes out. This is what we call induced polarization, just to explain it easier for ourselves as scientists, right? And then everything scales linearly. You put more light, this guy is stronger, right? But you don't change any frequency. Everything is linearly scaling. And it's all about this displacement, let's say, right? So now, if you have a strong laser, right? Now you don't have a bulb, but you have a strong laser. The force is strong, so you are a stronger person, right? The polarization that you induce is much stronger. And if you really scale it up, you go out of this linear regime. What happens in the linear regime? The force is not proportional to the frequency in the case of the spring, right? It deviates, right? This deviation, if you translate it, it's like generation of new frequencies, right? That's when the second harmonic generation happens. Third harmonic generation. If you put more light, you deviate more, and then you generate higher and higher frequency. Then you can expand everything and write it in this Taylor expansion, right? You can describe your polarization with terms. The higher the electric field of your light, the more intense your light, the bigger is this induced polarization. This regime is called Pondermotive regime, right? And this has been the Bloomberger Nobel Prize, right? That's what how he described everything. That how the relation of the electric field of laser and induced polarization in matter scales. Now, today, whatever I talked about, I was always at this regime. So the second sound frequency, no, we didn't talk about sound frequency. So the OPA, optical parametric amplification, is this term. Kerr effect, self-phase modulation. What else we talked about? If you do second harmonic generation, this historical paper that I showed, it's this regime, right? But then we talked that the CPA happened, and then with the CPA, the intensity of laser pulses became huge, right? So then scientists started to put this intense, very intense light onto the matter. You cannot shine it to the glass anymore because you damage it. That's why they shined it to the gas, right? And then in the gas, okay, you can't damage the gas, right? So then they observed non-ponderomotive behavior. It means that the behavior of this interaction was not, it wasn't possible to explain it with this formula. And that's the birth of the attosecond physics and high harmonic generation, which we talk about it tomorrow. But today, we just talked about this relation of a ball and a spring, like electrons, and what bonds them to matter, and how you can induce a polarization, and how scaling the energy moves you away from this linear relations.
We have the last question because we are late in the program. There is a question online also. So if I understand well, it is the vibration close to the or at the resonance that cause the nonlinear behavior.
If you read it again.
If I understand well, it is the vibration close to or at the resonance that cause the nonlinear behavior.
So then this is so important to distinguish. So if you are shining a matter at the resonance frequency, right? So this is the ground state, this is the excited state. This has the energy gap, right? If my laser, my photons, they have an energy that fit this energy gap, right? Then I'm going to absorb that photon and excite the electron to the excited level. This is what happens in laser, right? We actually really absorb the photons, right? You absorb a pump photon, put the electron there, you do the work, put the electron in a higher level, and then you try to harvest it in a laser or something. But in the ponderomotive regime and nonlinear optics, in some of them, yes, but on the one that for example, two-photon absorption, you really have an absorption. But in the ones that I just explained, you are at the virtual level, so it means that your photon energy is not enough to really displace electron and put it on a higher state, but you leave it somewhere in between, right? You just induce a polarization. And there, playing with this, you can do nonlinear, you can observe nonlinear phenomena. So you don't have actual absorption by the matter for the phenomena that I talked about. Because there is, for example, some nonlinear absorption, which is called two-photon absorption, right? So for the ones that I talked about, you are not at resonance, right?
There is one question for you. How long does it take to you to implement these different technologies?
Different knowledge?
Technology.
So then, again, it's all teamwork, right? So what I showed, hundreds of people contributed, right? Hundreds of scientists, even more, maybe thousands of scientists. And then if you look at the time scale, I can give you some, if I find my curve, okay. So you can see, right? It takes crowd to move a stone, right? So many scientists just failed and succeeded to move this curve to here, right? And now what I explained in terms of ytterbium-YAG technology is around here. So it's like a 15 years, 2-decade long technology. And it really takes a big family to move this stone. So it's not based on individual work, but many people contributed. All around the world, I would say.
Yeah, thank you. Let us clap for the speaker. Now it is break time. We go for tea. Then we come back 10:20. Thank you.
What we are having today is an ongoing training. It has been ongoing from Monday. It's going to be 5 days until Friday. And mainly what we are training people in is the installation of solar panels and every component that comes with installations from home. If anyone needs solar PV technologies, the panels, the batteries, the charge controllers, the inverters, and so forth. So from this training, the students that you are seeing in the back view are learning the very basics to begin with, from electricity, these components, what they entail, what are they going to look for when they go to purchase such items, or even before they purchase them, what do they need to consider from the place that they want to install them into. We are an avenue of creating job opportunities for the youth that take part in this training, because now they'll go forth with the certifications they acquire. They will acquire licensing to be able to install these technologies as technicians.
This week we have a solar PV training, solar photovoltaics training. It has started from Monday, 30th of November, and it is going for 5 days. So it's ending on 4th of December. So basically, we are instilling skills on solar installations, designing, and sizing. We have about 17 participants. Most of them are students from Multimedia University of Kenya, and they are really interested to know more about green energy technologies and solar technologies. After this training, they will be now skilled solar technicians.
I'm a third year student in multimedia, pursuing a bachelor's in renewable energy and technology. So this week we've been here in the T1, T2 training, which is a renewable energy research consortium. I'm going to be a participant. I'm here because I want to be impacted in my knowledge, and at the end of this course, I expect to be able to be consulted according to the solar PV installation, and I expect to have knowledge of installing myself and even assembling and coming up with new ideas to impact the world in terms of energy, concentrating on the renewable energy. The experience so far is very good. It's the third day, but I think I've gained more knowledge than I expected. Right now we are doing the hands-on, it's the practical unit, and I think they're impacting very well because it's easier to understand when it comes to the practical sessions more than the theoretic. And I think it is very beneficial to me so far.
The experience is good so far. At the end of this program, I expect to have gained more knowledge, to be able to understand how to install appliances, how to choose the correct appliances, how to deal with customers and their demands. The experience has been very inspiring, being that there are more female students than male students. Actually, it's actually a great honor. So, yeah, the program so far has been good.
It has been a wonderful experience as an intern here. I've been an intern for the past 1 year since the consortium was established, and it has been a continual educational and a learning process. When I see myself wearing an overall, when I see myself carrying a solar panel, when I see myself connecting a battery to power the loads, it has been a wonderful experience being part of the consortium. And next to it, we are proud and even more happy to have the first T1, T2 training, solar PV training in MMU. It has been a wonderful journey since the consortium was born, and as you can see the growth, and even having the first T1, T2 training, it has been a great milestone. It has been a wonderful reception, and the students getting, or rather the trainees getting to understand and to attach what they have in class and what is there practically. I'd like to urge those in the science and engineering courses to flood up these trainings, mostly from MMU or rather any other institution, from any other company in the energy sector. They can come to obtain the skills that are in line with the trainings that we have.
This week is a landmark for us because we are having the first T1, T2 solar workshop, whereby we are focusing on our young youth, especially the science and engineering students. And so far, so good. We had a very good feedback, whereby we have a total of about 16 young men and women who have joined us in this workshop. We expect them at the end of the workshop to actually just apply what they have learned, and of course get licenses from the energy sector. At the same time, we are also working in partnership with the educational institutions in Germany, whereby we are collaborating into these hands-on skills. And I want to welcome all of you, especially those who are in the energy sector, to join us to actually be part of this consortium. The main aim is to actually equip the hands-on skills to these young, consultants. And one of the skills is the sizing, how they are going to size these solar components. As you are aware, we have had a challenge when it comes to malfunctioning of the solar components in our domestic and industrial sector. At the same time, once they get licensed, we expect that as a university, we are going to actually do a pilot project of a solar PV plant within our institution, and also do awareness workshops within our community, just to make sure that we do actually the correct sizing of these solar components within our nation.
Hello, I'm Collins Bet.
And I am Victor Kimaru. Greetings from Multimedia University of Kenya, National Institute for Optics and Lasers. My name is Professor Geoffrey Kihara Roremo. I'm a professor of physics, and in particular optics and lasers. I am going to give you an overview about Multimedia University of Kenya and also some very important information about the National Institute for Optics and Lasers, which is going to host the East African Summer School in Optics and Lasers. Multimedia University of Kenya was established in the year 2013 after getting the charter from the then President of the nation. At the moment, the university has 6 faculties, and these are the Faculty of Science and Technology, Faculty of Engineering and Technology, Faculty of Business and Economics, Faculty of Media and Communication, Faculty of Social Sciences and Technology, Faculty of Computer Science and Information Technology, and also an institute, which is the National Institute for Optics and Lasers. I'm going to give a bit more information about the Institute for Optics and Lasers, which was established in the year 2019. At the moment, the institute offers 2 Masters of Science programs, Master of Science in Applied Optics and Masters of Science in Laser Technology. This is the only institute of its kind in Kenya and also in East and Central Africa. At the moment, the institute has a population of 30 students who are in their different levels. Some are currently doing research and others are going on with their coursework. At the National Institute for Optics and Lasers, we are having quite a range of projects, and we are going to explain all this during the summer school, the East African Summer School in Optics and Lasers. We are going to give the participants a good overview about the kind of research that we are doing. So I would like to welcome all of you to come and attend the summer school, and indeed you are going to benefit a lot as you get exposed to the current research activities that are happening at the global arena. You are most welcome, and see you at Multimedia University of Kenya between 6th of May and 17th of May 2024. Thank you.
Let's restart the session, please. We have a 10 minutes delay.
Greetings from Multimedia University of Kenya, National Institute for Optics and Lasers. My name is Professor Geoffrey Kihara Roremo. I'm a professor of physics, and in particular optics and lasers. I am going to give you an overview about Multimedia University of Kenya
and also some very important information about the National Institute for Optics and Lasers, which is going to host the East African Summer School in Optics and Lasers. Multimedia University of Kenya was established in the year 2013 after getting the charter from the then President of the nation.
Okay, let's start
University
the
has
session.
6 faculties.
Welcome to Multimedia University of Kenya, a center of excellence in engineering, ICT, and business studies.
Stop the start.
This is the iMac lab.
Okay, let's start the section. Our next speaker is Alessia Candeo from the Politecnico de Milano, and she will continue the talk about advancing imaging technology. Then, Alessia, the floor is yours.
Can you hear me? Ah, okay, yeah, perfect. Sorry. Okay, so hi everyone. Today I'd like to first finish my presentation from yesterday that, if you remember, are all the students back already? Just to, because I see many spots that are empty. Do you think that they're all there? If they do, I will first finish the talk I started yesterday. Okay. All right. So the talk yesterday, if you remember, was about light sheet fluorescence microscopy, and it was a technique that we developed to be able to illuminate our samples with a blade of light, just a full plane of light. We excite the fluorescence from the whole 2D plane, and then we detect the fluorescence and acquire an image at 90 degrees with respect to the excitation axis. And in this way, by recording the images with a camera, we are very efficient in the illumination and collection. So we can use doses of light that are lower compared to other standard methods. And we can go faster compared to, for example, confocal microscopy or two-photon microscopy. So the idea is to be able to create three-dimensional reconstructions of three-dimensional samples that also might move for some reason, either because they are highly motile or because something is changing in the sample. For example, there is a development going on, or we want to look at calcium variations, ions exchanges in the cells. So that's a little bit the idea. So today we'll talk a little bit about the implementation, the data analysis, and the applications, which is the most interesting part. And then we will move on to another subject. So first of all, I'd like to mention that this light sheet fluorescence microscopy technique is actually being, it's something that I'm not the only one that does that. There are many people doing it, and there is also a lot of information online about open source projects. For example, the OpenSpin project, where basically on the website they show you how to build your own light sheet microscope. There is the list of parts that you have to buy if you want to make one. So it's very nice because it allows you to very easily set up your microscope. There is also another one that is this OpenSpin microscopy open source project, which is similar. So you have choices. There is even a Lego. I don't know if you know Lego light sheet that you can build with Legos. It's very nice. From the point of view of the acquisition, though, I didn't say much yet. But if you think about it, I said that we acquire many, many images to obtain a three-dimensional reconstruction of our samples. And I also said that we would like to monitor our samples a long time. So we might collect many images to create a three-dimensional reconstruction, and then we want to do this multiple times. Okay, so in this way, we collect thousands of images. And so if we collect, for example, images at 100 Hertz with a 16-bit cameras with 2048 pixels, even if we sum some of the pixels to reduce the dimension of our data set, and we record for 1 hour and a half, we get to 1 terabyte. Okay, 1 terabyte of data in half an hour. And actually, we can collect even larger data sets now because we have cameras that with more pixels, and we can go faster. So this is a little bit tricky if you think about it. Even opening your data set after the acquisition is terrible. I mean, my computer cannot deal with it, for example. You need cluster computing to be able to even just open the data set, not to mention analyze it. So this is very heavily consuming your resources. It's a task that is very hard to do. And so what do? We think in advance. And we record only what we need. So when you do microscopy, and some microscopies like light sheet fluorescence microscopy, where you can end up with huge data sets, you need to plan very well in advance your experiment, because otherwise you're going to obtain a data set that you cannot use. So planning in advance your experiment is fundamental. Okay? Understanding the problem, understanding what you want to obtain is really important, because otherwise you just waste time and resources. And for the data handling, in fact, there are also online and also open source. Even in this case, the light sheet fluorescence microscopy community is very nice from this point of view. There are quite a few softwares that you can use that already have plug-in developed by other software developers. Like ImageJ or Fiji. These are open source softwares that you can use to open your images. Then you can code in MATLAB. Right now, the community is moving towards Python. Then we have other softwares like Elastic, Imaris, or Napari. So there are many different softwares that you can use to analyze your data, but you can also develop your own plugins and develop plugins for others. There is big money right now put into image analysis, because when you have such large data sets, you have to find new ways to handle the data. And also this ends up also, let's say, fostering, let's say that this as, let's put it like this. A lot of data sets, a lot of plugins, a lot of software development that has been done for image analysis has ended up in the big data industry, in the AI industry. So it's something that is really connected to all the big developments that are going on AI, data mining, and so on. So this is something that can have impact not only in image analysis, but also more in general in software analysis and development. And when you have your data set, when you collect your data set, you have to do few steps that are quite, let's say, standard. Like you need to, first of all, be able to visualize your data set. Then if your sample has moved during the acquisition, you might need to register your images. Then if you acquire multiple views of your sample, you might need to stitch the tiles that you acquired or the multiple views. You have to fuse them together. If you don't like to have the stripes that I talked about yesterday, when you have something that is absorbing your laser, you have to do a stripe removal algorithm. And then if you have something that moves and you want to track it, you have to segment your image and then track it. And if you want to make your image look prettier, you might also want to deconvolve your image, but that's a whole different story. That's just for, in my opinion, is just for, let's say, having prettier data, not more useful data. So we go back to the sample I showed you at the very beginning of my talk, and this is the shrimp that basically was imaged for 4 days. So the overall development of this shrimp was observed for 4 days, okay? And they collected this. I didn't collect this data set, just to be clear. And who collected it? Collected 7 terabytes of data. So it's huge data set, and they were analyzing this data set to cluster computing in different parts of Europe. So different labs in Europe were taking care of different steps to try to be as efficient as possible for the analysis of this thing. So what did they do? They had to register this data set because the sample was moving. You saw that it was rolling, for example. So they had to pre-process all the images to first export them in a format that could be used by everybody. Then they had to do the registration of all the time frames, okay, all the frames, because the sample was rotating, was moving, so they had to realign all the frames. Then they had to put them all together, fuse them together, because they took different angles of view. And then they had to fuse the volume. Then they had to do the rendering, which you just saw. That took ages, okay, it took months to do. Maybe right now with the new cards, new NVIDIA cards would be faster, but when they did this, that's what happened. And then they tracked the cells. So why was this useful? Because they tracked the cells from development to the limbs formation. So they went on in time. They look at the cells that were developed as limbs, and then they went back in times. And they tracked those cells back, and they went back to understand which cells were the primary cells that originated the limbs. Okay? So this was very useful to understand the genetic of this animal, which cells have the genes that will develop in the end as limbs. Okay? So it's quite nice because in the end they could pinpoint the single cells that by dividing by division generated all the limbs of the shrimps. So talking about samples now. So I'll show you some samples that I've been analyzing throughout the years. Okay. This big one with this pretty one, in my opinion this is very pretty, is a spheroid. So spheroids, I mentioned them yesterday as well. They are just agglomerates of cells that, okay, you know, usually when you look at cells, biologists put the cells on a slide, on a flat surface. They are monolayers. They are not really representative of tissues, though, okay? They are useful, but not fully representative of tissues. So what we do, we create models to resemble tissues, or even, for example, solid tumors. So we take cells and we make them grow as balls. They are balls of cells, okay? And then with this technique, we can visualize this three-dimensional object, for example. So we start from the cells. So you can see that we have good resolution because we can see single cells. These are single cells that are circular because they were suspension cells. And it was possible for us to monitor a long time how they move, for example, how they roll and how they attach to each other when they are on the surface of a gel. Okay, this was interesting because we wanted to look at the attachment, how the cells attach to gels. And then what we can do, for example, is study how the cells grasp onto the gel or onto different types of material. And we can look a long time if they go in depth inside the material. So the idea here was to try to obtain a scaffold for the cells to develop in a way that resembles a tissue. Okay, so the idea is that the biologist here was developing this material. He had the cells. He put the cells onto the gel, and he wanted to see if the cells were colonizing the gel a long time, and if they were going in depth in the gel, to see if, in the end, they would create a tissue. So with this technique, this is something that we can do easily. This is the spheroid. You can see that I'm going through the spheroid, okay? So I'm taking many images through the spheroid. The spheroid is a sphere, so I went from top to the center. This is a central plane of my spheroid. You can see here it's very blurred. This is scattered light, okay? So I cannot really get much information here. But I can see very nicely what happens on the surface, for example, with 150, within 200 micrometers, depending on the material, or the type of cells that we use here. And some of the fluorescence here in the center of the spheroid, even though I don't have real good spatial resolution, I can still infer some conclusions. For example, now I will show you some results on the study of spheroids that I did. So first of all, these are nuclei, okay? So these are the nuclei of the cells that were stained with a specific biomarker. And a long time, what we saw was, for example, that these cells were very happy and alive because they were forming these filaments, that is the filaments of the DNA that is creating new cells. So a long time, we could look at cell division. So these spheroids, they behave like they keep on growing. They form, and then they keep on growing very large. And what we can do with this, we can, for example, take a spheroid that right now you cannot see because it was not stained, and we can put, for example, a drug that is fluorescent. So the spheroid you are going to see, it's a spheroid that resembles a tumor, solid tumor, and we put a drug that we thought was, let's say, useful to try to destroy the tumor, and this drug was fluorescent, and this is what we observed. So for example, we can study how the drug goes inside our spheroid, so we can monitor the drug kinetic, the drug administration, but you can see now that it's inside. It went from the outside. Now, even though here we don't have a cellular resolution, we can see that it went inside. And this is from the top, and those are lateral views. So it's quite nice that we can study how the drug can penetrate in the spheroid a long time. And I don't know if you noticed, but this spheroid got larger. It got larger because it was actually breaking apart. So a long time, the spheroid breaks apart. The drug works, of course, still, unfortunately, it's a long, long way. It's one of those, of many other drugs that might work in the future for solid tumor treatment. But the nice thing is that if we compare what we can observe, the drug kinetic speed of, let's say, penetration in our spheroid when we study monolayers, so standard glass with the cells on top of it, this is what you get, just one single curve. But with this technique, we can study what happens at different depths in the spheroid. So we can, so we have a deeper understanding of this process because we can study what happens at the surface, but then that's very different from what happens in the center. Okay, we want to reach the center of the spheroid. So this is useful to, try to understand if a drug is actually going to go inside a solid tissue, a solid tumor. And then I've done a lot of studies on plant roots. That was most of my PhD was actually light sheet on for the study of plant roots. So plant roots are transparent, okay? So we can easily look at them with light sheet fluorescence microscopy. And the idea is that we use this plant as a standard in plant biology. It's called Arabidopsis thaliana. And it's a model plant because it's very easy to handle, the life cycle is fast, and the genome has been sequenced like in early 2000, and it's fully available to all the scientists. So this is a plant that can be easily genetically modified, for example, in a standard way. So what happens? It happens that the biologist, not me, the biologist takes the plants, modifies the genes, and makes them fluorescent, for example. And then maybe he says, okay, I want to study a specific gene. If I remove that gene, the plant is going to behave in the same way or not? And if it does behave in the same way or not, then we can maybe say something about the role of that gene in the response, for example, to a stimulus. So what I'm interested in are the roots. The roots have, this is the root tip of a plant. And I don't know if you can see, but also the plant roots are very hairy. They have hairs, okay? They have hairs. These hairs are very important for the plant because that's what makes the roots stick to the soil and absorb nutrients. So we study a lot these plant root hairs. So this is the same root tip. It's just reversed. And this is fluorescent because the biologist has modified the plant. And in particular, the fluorescence is sensitive to the concentration of calcium ions in the plant root. Okay? So if we see a variation in fluorescence, that's because the ions of calcium in the root have changed their concentration. So the biologist looked at this image. This is a wide field image. Okay, it's a time lapse. So he looked at this plant root and he saw that when he was administrating some sugar, there was a variation in calcium concentration because I'll show you again. What happens is that you have a variation in the fluorescence. So the color change tells you, okay, something has happened. The plant has responded. It has realized that something put sugar in the water. But what the biologist wanted to understand is, what I've seen is diffusion of the sugar inside the plant, or is it cell communication? Okay, so because cell communication means that the information is passed cell by cell, we need to be able to see the cells. Here, we don't see the single cells because the root is thick. Okay? So we need something that gives us three-dimensional resolution. Confocal microscopy is an option, but it's slow. So we developed the light sheet fluorescence microscope just for our plant biologist. This is similar to the one that I'll build in the experimental room. And yeah, this is just a schematic, but the nice thing is that this is how we mount our samples. So I told you yesterday, with light sheet, we need to find new ways of mounting our samples. And sometimes it's a good thing, because for plants, they prefer to stay vertical. Like in this case, they are growing in these tubes. The tubes are made of FEP. It's a plastic that has the same index of refraction of water. And there is a gel, agar gel, inside here. And the plant grows inside the agar in a three-dimensional arrangement. If you use another standard microscopy technique, you have to put the plant horizontal. Plant doesn't like that. Plant doesn't like staying horizontal. Root hairs, they are floppy. They don't like that. They really like, instead, staying vertical like this. So light sheet was a very good idea. So again, this is what we see with standard microscopy. Let's see now with light sheet. So first of all, you see these are single nuclei expressing the same fluorophore. So when we administrate sugar, that's what we see. Okay. I think that was super cool. I don't know if you do as well. But the cool thing, I'll show you again, is that we can see a calcium wave. So variations in calcium concentration give you this variation in color. And we can see that the information about the stimulus propagates from one cell, to all the others, and it goes in a specific direction. And I can even tell you that this is the first cell that felt the stimulus. That's because that cell has the receptors for sugar. While the others maybe no. Maybe they have other receptors. They just get the information from that cell because of the calcium variation concentration. But this is very interesting because then we now know that there is cell-to-cell communication in plants. And then we can repeat this experiment with many other stimuli. For example, here, again, this is sugar. This could be salt. It's actually ATP, but we don't care. And we can say, OK, let's see if the plant responds differently to different stimuli. So let's see. So the one on the left brights up. The other one does as well, but slower. It takes longer. So the plant responds with a specific fingerprint to different stimuli. It means that it can recognize the different stimuli. And how does it encode this information? Well, it encodes it with this type of different calcium wave. Okay, so a faster one when it's about glutamate, and a slower one, a longer one, when it's, for example, ATP in this case. And the other interesting thing is that we can select the same cells on the surface of our plant, for example, and different cells, for example, these two cells, here you see they don't respond in the same way to glutamate, but in this case, these are the same cells. They respond in a very similar way to ATP. So it means that they have both the same receptors for this stimulus, but not for this sugar stimulus. Okay? So in this way, we can understand where the receptors for different stimuli are in the plants, where they are localized. We can do that very precisely. And then we can take a plant and we can remove the genes, some of the genes that I want to study, and we can see, we can test and see if the plant still has the same responses. And if it does, OK, well, that gene was not involved in the response to that stimulus. But if instead the response from the plant changes, then, OK, then that gene was involved somehow, because things have changed when I removed the gene. OK, so this is how we do genetic studies on plants. And then you can also, for example, if you remove these genes, one of the genes that you are interested in, OK, you might look also just at the 3D with the light sheet to infer some, to say something about the phenotype. So what's the phenotype? It's just the arrangement, like the way the plant looks like when you remove a gene. So this is the phenotype of a wild-type plant, standard plant, and this is a mutant plant where we removed one of the genes, and you can see that the root hairs, in this case, are different. So here we are looking at root hairs now, okay? So here they are very nice, they are tidy, they are, okay, all pretty. Here they are very ugly. I'm not sorry for this body shaming of the plant, but they are ugly. They are branching, they are really, something's gone very bad with that plant. And all the plants with those, without the gene, that specific gene, were like this, similar, okay? They were branching, they were, sometimes they were breaking. There were also less in number. So the gene that we removed was involved in the fact that the plant was developing healthier. And healthier are important for the plants, okay? Because if they are healthy, the plant can grow well. Okay, so why do we want to know if the genes give us good root hairs? Because we want to try to improve plants' genetic to be able to develop plants that can grow, for example, in harsh environments, okay? Plants that can grow where the soil is poor, for example, where there are not many nutrients, for example. So the idea is to try to improve crops' yield in the very end. So if we now look at something that happens on the root hairs a long time, so I want to say that this experiment, this specific experiment, we did it in 2013. Okay, we were one of the first to see this. I'm not boasting about the fact that we were the first, but the reason why we were the first is that we were the first to randomly put a plant in the light sheet fluorescence microscope. We didn't know what to expect, okay? So we didn't plan this experiment. I said that you have to plan. This one we didn't. We didn't know at the time. And this is something we found out. We just saw, okay, what's going on at the root tip, at the root hair tip? So I'll show you again. So look at the root hair tip. What's going on? Why is there blinking? Something's going on. It's very weird. At the root hair tip, you have calcium oscillations. We realized that these calcium oscillations were periodic. They looked like sine waves, okay? They were all the same in all the plants. They were all the same frequency of oscillation. We were like, wow, this is great. So this means that root hairs that are healthy have that specific signal, that specific variation in the calcium concentration. So what happens with our mutant, our ugly mutant? Okay, the ugly mutant has really bad root hairs oscillations. Okay, so the gradient of calcium that we have is deregulated. This means that the gene that we have removed was involved in the correct oscillation, oscillation of the calcium gradient at the root hair tip. You see that these signals are different. And then we could even analyze this in Fourier transform domain and do proper statistical analysis, but I'm not going into the details of that. But I'm still doing those experiments with different plants. This is something that is being very rewarding for us. And then I will move to zebrafish. Now let's change completely the subject. Zebrafish. Zebrafish is another model organism that we study because they are vertebrates, so they are pretty, well, they are not mammals, of course, but they are better than cells, better than worms. They are vertebrate. They also are usually used as models because their genome is, again, fully sequenced. They have a fast reproductive cycle, and they are transparent at the larval stage, okay? There are some that already have pigments, okay? But if we select the right zebrafish lines, for example, the pearl or the albino, they don't have pigments, so they are pretty transparent, apart from the retina. You don't want to use you don't want to do laser surgery in the eyes of the zebrafish, so those are places to be avoided, the eyes. Okay, so they have 80,000 neurons, and they are behaving. What do I mean when I say behaving? I mean that they do things. Zebrafish can do things, okay? So we want to study them, and I will start from the fact that their brain is very useful to be studied because it gives us some insights in the circuitry, in the neural circuitry. Okay, so they somehow, by studying the zebrafish brain, we can also do extrapolate conclusions on how, in general, neural networks do work, okay? So to put zebrafish in a light sheet system, we need to somehow fix it. And as yesterday we were mentioning, we put it in agar again, and basically what I do, I melt agar, which is just gelatin. I put the zebrafish inside, and then I suck it up with a syringe, in a tube, in a capillary. I wait for the agar to solidify, and then I might remove part of the agar. So I extrude it from the tube. The tube is here. And then I cut this part of the agar so that the zebrafish can still move the tail and think that he's swimming. He's not really swimming, but he thinks that he's swimming. So I head fix it, all right? So when it's head fixed, then we can play with it. And we can look at what happens at the neurons in 3D. So we can look at neuronal activation in the zebrafish. And we can decide if we want to study let's say, spontaneous activation to understand how spontaneous connections are made. Or we can also do, let's say, evoked evoked activity studies. What does it mean? It means that we evoke a behavioral activation. In the case of the zebrafish, they cannot do many tasks. But something they can do very well is see things and swim accordingly to what they see. They also can catch prey. So we put the zebrafish in a virtual reality. We make the zebrafish think that he's swimming by projecting at the bottom of the zebrafish a grid, and we move the grid. And when we move the grid forward or backward, the zebrafish thinks that he has to move the tail because he sees things moving, so he's moving the tail as a response. So the zebrafish responds to your specific stimulus. And then if we rotate, so this is the response, but then we can also rotate the grid. And the zebrafish will think that it's turning. So it will move the tail in a different manner. Okay, so every different angular movement of our grid will generate a different effect in the mind of the zebrafish, and hence a different brain activation. Okay, and so we analyzed the data set. It was a large data set, but that's not important right now. The point is just that we could extract we could extract the fluorescence from each of the neurons in the zebrafish brain, and we could correlate the specific signal that we were retrieving from the zebrafish neurons and correlate that with the orientation of the grid, okay? And because, thanks to the technique, we can look at different brain areas at the same time, thanks to the large field of view that we have, we can correlate what happens here, which is the visual area, and the motor area, and the decision-making area, okay? So this area, that is the visual area, is always active. So here it's basically white, because the zebrafish is always seeing the grid. But then this part of the brain is more active when the grid is oriented in one direction. When the zebrafish sees the grid oriented in the opposite direction, we have activation of this other brain region. And when the tail moves, we know it because these other neurons activate. So we can correlate what the zebrafish sees and which neurons activate before and after, and why, because we know also the evoked stimulus that we are giving, that we are delivering. So this is a very nice study that we did in orientation selectivity while I was in France. And then we can do zebrafish development for what concerns the cardiovascular system, for example. Here I showed you already this video of the zebrafish developing his cardiovascular system for 3 days. But I think it's quite interesting also if I show you this one. So this is how we keep the zebrafish in a tube, in this case, where there is a very low gel, very low concentration gel, so it's almost liquid. There is just a little bit of, let's say, constraint to the zebrafish, because otherwise the zebrafish would not grow properly. Okay, if we don't mount it correctly, the zebrafish dies. And we can follow the growth, the development of the zebrafish for a very long time. And then again, in this case, we have a wild type, which means a healthy zebrafish. And we can compare what happens now from the projector. Unfortunately, it's not very clear, but the idea is, for example, this is what we got from a zebrafish where we removed a gene that we believe is involved in correct development of the cardiovascular system. And in fact, the cardiovascular system of this zebrafish is all messed up. So, poor zebrafish. But then, of course, the idea is that we administrate the drugs to try to solve this problem, to try to develop new types of medications for people that have, well, zebrafish and people that have maybe cardiovascular disease, okay? So these are all models for this type of studies. We have other samples that are even bigger. This is, for example, Hydra vulgaris. It's like a polyp. The problem with Hydra is that it moves a lot continuously. This is a mess. It's a really difficult sample. I have a grant on that, and I don't know, I'm going to, yeah. But okay, so this is the Hydra that is moving a lot. And we use this as a model for regenerative studies. The Hydra is that animal that when you cut it in two, you get 2 Hydras. If you cut it again, you have 3 Hydras, and so on. And the Hydra keeps on regenerating. So it's a good model for regenerative tissue studies. And in fact, we managed to basically observe a long time how the tentacles can regrow, and we analyzed the formation of buds from the stressed hydras. And of course, also in this case, we gave some treatments to the hydra to see if we could speed up this process of regeneration, or maybe we put some nanoparticles inside the hydra and we illuminated it with IR light to see if heat can improve regeneration in the tissue. And so in general, this is something we can easily do with this microscope because we can mount the hydra very easily. We can record for long times, and we can keep the sample alive for long. Then we have done studies also on fixed samples. For example, this is an intestine of a mouse that was cleared in the way that I mentioned yesterday. And the idea here was to study the arrangement of the villi, of the structure of this piece of intestine as a function of the diet of the mouse. So some mouse were gluten intolerant, okay? And so we looked at the arrangement of the villi when the mouse was healthy and when it was, for example, had problems with gluten, and then in both cases what was happening with different types of diets. Okay, so this is something we can do as well without cutting. I forgot to say, without cutting the intestine. Okay, we have to cut it into pieces because it's very long, but without opening up. So the intestine keeps its shape of this tubular shape, and here we have opened it virtually after post-processing with the computer. And well, I think I'm done. No, okay. If let's see, this is the last slide. So if it doesn't work, it's not a big deal. Okay. So the very last thing I'm going to mention is that we can also do fluidodynamic studies with the light sheet because of the fact that it's very fast. Okay, so because it's very fast, we can monitor, we can look at particles moving through tubes that we have tailored, for example, in this fashion, to basically to see if what, is it me? No. So basically, the idea is that we create fluidodynamic chips, and we want to study the fluid dynamics of the particle that moves in these chips. And we can do that very easily with the light sheet because we can go very fast and we can look in 3D if what we have created actually is, it behaves as it should when when you perform simulations, okay? So this is a different application for material science. For example, if you want to study how a material behaves when it's subject to constraints in fluidic channels. So with this, I think I'm done. So, well, I don't think I need to go through the conclusions, but if you have any questions, I'd love to, maybe we can do now the 10 minutes.
10 minutes question.
Yes.
Question, please.
Yes.
Thank you for the presentation. My question is, the samples are in a fluid, and
Yes.
does the pH changes over time? So do you take into account pH changes within the fluid where the plant is, or the zebrafish, and how this affects your measurements?
Right, that's a very good question. Yeah, this is something that is extremely important, and I realized only after many failed experiments that pH is something that is you have to take into consideration. So it's not very important when it's about zebrafish, honestly, because zebrafish they are quite evolved, so they don't care too much about the pH for at least for the changes that take place during the experimental time. They don't affect the zebrafish. For plants, we need to be more careful, and in fact, we do change the medium with a pump if we do more than a day, because then, yes, the pH can affect, it does affect the plant. The idea is that you need a change that is that your system can perceive. So for the plant, it takes a day to perceive that, and so we do change with the fluidic pump the medium. But with cells and spheroids, that's fundamental. That's very important. So basically, if you have your cells so cells are very sensitive to everything, okay? They are very fragile. So they are sensitive to temperature, they are sensitive to oxygen, to the concentration of oxygen, to the concentration of CO2, they are sensitive to pH in the medium, how the medium is made. So you need to be very careful. In that case, we always had a perfusion system to keep on changing the medium. Well, not at the beginning, which was why my cells were always dying, but yes, then we had to put that in place. We had to control. So when you do experiments with cells for a long time, you need to have a chamber that keeps the cells at a specific humidity, a specific CO2 concentration in the environment, specific temperature, and pH is important, so yes, you have to change the medium, otherwise the cells don't survive. Or they do something that is not what you should be seeing. They are, okay, thank you for...
Okay, you have a question here, one question over there.
Yeah, thank you for the presentation. I would like to have a clarity on the grid, where you are saying how the zebra moves, and why the grid? Can't we have any other thing else that can help maybe the tail to move?
Sorry, I didn't understand. Can you repeat the question,
I'm
please?
saying there is an aspect where you spoke of the grid.
Okay.
Yeah, the grid where it forces the zebra to move.
Yes,
Yeah.
yes.
So I need to have a clarification on that, and maybe why the grid? Can't we have any other thing else?
Okay, yes.
And maybe a question number 2.
Yes.
What are the specifications of the test tube that you are using?
Okay.
Yeah.
That's good, yes. So why the grid? Well, the grid is the easiest pattern that we could, it's the easiest, it's a very clear pattern for the zebrafish. So the zebrafish sees that easily. And we know also the grid is like a standard that is being used in this field of behavioral imaging in zebrafish. So it's because it's, you have stripes of dark and red. Actually, the grid is made of dark and red because the zebrafish has red, the sensors in the eyes for red, for example. No, I'm sorry. The zebrafish, well, whatever, doesn't matter. Let's not talk about this because it's complicated. Anyway, so we have this grid because, yes, it's a very, the stripes are very visible for the zebrafish. So, yes. But in principle, they can see other patterns. In fact, there are other people that do studies where they look at how the eyes move. Okay, so they track the movement of the zebrafish eyes when they are subject to evoked stimulation with dots, okay, on a screen that is in front of them, and these dots resemble prey. So the zebrafish thinks that is catching prey. So also dots are something that the zebrafish can follow, but it wouldn't swim, for example, if it was seeing a dot. It would go towards the dot because the dot resembles a prey. While instead with the grid is a very visible pattern, it's very large, and the zebrafish clearly see the grid, and it moves, and we know that that happens. There is a lot of literature on that, so that's a standard as well. So on the other note, so for the power, that's a very good point. The power is very low. So what I mean with low, for plants, we are talking about tens of microwatts. 100 microwatt is already a lot of power, microwatts. So you need very little. Of course, we are also using very efficient cameras, for example, but you cannot use a power that is too high. Otherwise, you are going to affect your sample. We have done, so when we do experiments, when we start doing experiments, one of the first things we do is we test the bleaching. So we do tests at different laser powers, and we look if there is anything going on, if there is a trend with power, if there is something that happens with increasing power. And if there is, then we try to avoid that power. We go to a lower power. We use the lowest power possible. So this means that our images are not the best because the signal-to-noise ratio is just right to be able to extract the information we want. We don't want the best image. We want an image that is useful. So to get the best image, you need to have a very good signal-to-noise ratio. But maybe to get that, you also need to use a lot of power. We don't want that. We want to have the least amount of laser power, so just about right to have a decent signal-to-noise ratio that gives us good data. For the zebrafish, we can go up a bit. So I was using 200 microwatts. Okay. Well, no, actually a little bit more. For the experiment you've seen was about 500 microwatts. But still, it's quite low, also because it's dispersed on the light sheet, so it's not focused in a dot, it's on a plane. And then, yeah, but those are more or less the amount of powers that we use. So less than a milliwatt. So always less than a milliwatt is already too much if you want to do long-term time-lapse imaging. If you want to take a shot, okay. But on the long term, you need to use the least amount of power. And yeah, there was a question over there?
There's a question online.
Oh, okay.
Depending on
Sorry.
the experience, can we use the microscopic image of the roots to distinguish the physiological state of the plant?
Yes, we can. Yes. So that's what we do. So we have many. So for example, when we do screening of plants, what we do is we take the plant, we put the plant in front of the microscope. In principle, even already, most times, already with a standard microscope, you can say something about the physiological state of the plant, because if it is healthy, the phenotype will be the same as the wild type, but sometimes it's not enough. Sometimes, for example, you might think that the plant is healthy, however, maybe the root hairs are shorter than they should or longer than they should, and that you can understand when you look, for example, at the oscillations, or if you do, in general, more in-depth studies of how the plant behaves when subject to specific stimuli. Maybe you want to change the temperature in the environment and see how the plant reacts. But definitely, yes, you can infer information from the roots. We are doing a lot of experiments we call them rhizotrons. So we basically look also in crops, not only in these model plants, but even in crops now. We are looking at the arrangement of these of the root system. It's really an interesting one.
We have a question here.
Yes.
Yeah, thanks for that excellent presentation. I have about 3 questions.
Please.
Now, the first one is, when I look at the data that you acquired, within a short time you achieved that 1 terabyte mark.
Yes.
Is it possible to deploy some compression algorithm during acquisition so that you limit that?
Mm-hmm.
Then the second one will be, for example, the calculation was based on 16-bit camera.
Yes.
Suppose you used a 12-bit camera.
12, okay.
Is there some additional information that you're losing based on the fact that you're acquiring so many images? Then number 3, how feasible is it to maybe do some small work on this area using a Lego kit based on this amount of data that you're acquiring?
So I didn't understand this last one. Can you repeat this last question?
In your presentation, you mentioned that there are even Lego kits.
Yes.
Lego kits, right?
Yes.
So I think the Lego kits are for children to play around, if I'm not wrong.
Not necessarily.
So is it possible? Is it possible? How feasible is it if, for example, I wanted to do some small work using a Lego kit in my lab
Okay.
do the same work with a Lego kit.
Okay, I see. Okay, so I forgot the first question now. I'm sorry, can you, was it?
So we can go by one by.
Yes, please.
Then number one,
is
it possible to deploy compression
okay,
algorithm?
sure, yes, it is. It is possible. Some cameras, for example, have some cameras have a little bit of their own system of, they have like a small processor inside the camera. So what you could do is record for, use the memory of the camera, just the camera, without even putting the data on the computer, and with the camera immediately process those data, and for example, look for differences, do some kind of autocorrelation between images, and maybe you are interested in variations, so you basically discard anything that doesn't have intrinsic variations, okay? So something that people do is they actually acquire blocks of data, and they quickly analyze blocks of data, and if they are interested in variations in signals, if there is no variation, they just don't even save it on the computer. Another thing you can do is, yes, you can compress your data when you have empty pixels. For example, if you have dark pixels, you can just say, okay, those pixels I don't save. So there are ways, there are some compression files where basically the information that is stored in the black, completely dark pixels is not saved. So for example, HDF5, it's a new format that is being more and more used, where the way that the informations are saved is different compared to, I don't know, GIF, JPEG, TIFF, and so on. So there are ways, definitely. Am I the expert on that? No. But maybe if you are interested, I could give you more details. Another thing that we do, for example, when we have to collect things that move, we online, during the acquisition, we look for variations in the images immediately, and we record only the areas, ROIs, where the variation had taken place. Okay, so let's say that you have your image, something that comes up quickly in the image and then disappears. For example, a cell has passed through your light sheet and you see it. Well, you can tell to the system to acquire only the region where the variation has taken place, so that you can reduce the amount of saved data. Another thing that I do, for example, sometimes I don't record all the images, I record the sum of the images. So I sum all the images to create kind of a maximum intensity projection, we call them. And we don't save the stack, because that would be too many information, and we only save a maximum intensity projection of the stack, and we keep only the maximum intensity projection, because we believe that for what we are doing, that's enough sometimes, not all the times. So yes, you have to think in advance what to do. Another thing is that, okay, you save your data, and then you know you have to spend money on a cluster to analyze the data. But yes, there are ways to reduce the amount of data. Compression algorithm, smart acquisitions. What was the second question?
Okay, the second one was still based on the same. For example,
the 12-bit camera.
Yeah.
So the problem is that, of course, with less bits, you have less levels of gray, and so maybe the signal-to-noise ratio is worse. So we usually use 16-bit cameras because you have more levels, and having more levels help you to have a better signal-to-noise ratio. So we do use also, for some applications, we use lower, let's say, cameras that have lower performances, like even 8-bit cameras sometimes. But in that case, maybe we are not interested in having a very detailed image. Okay, maybe we look mostly at differences. Let's put it like this. And in that case, a camera with less bits can be enough. But what you lose levels. So you lose a little bit of contrast, of image quality. And I can say there is this new camera that I really like, I really want, which is called event-based camera, where you have just 2 bits, 3 bits, something like that. It's a very cheap camera, well, cheap compared to other scientific cameras, where basically it's a camera that looks only at variations directly, and it gives you +1, -1, and 0. It gives you informations only, basically it activates when there is a variation. If you have a variation in signal, you have a pixel that becomes white, or to +1 or -1 if there is a negative variation. That's an interesting camera. So for the third question, what was it? Ah, the Lego. Vabbè, okay. So I wouldn't use a Lego light sheet for these experiments because, I mean, because the way I've seen the Lego light sheet being implemented, okay, it was mostly for demonstration purposes. But could you build a Lego light sheet after all, if you use good optics and so on? I think so. I mean, there are people that build light sheet with 3D printing. There is a project that was discussing this yesterday. It's called UC2, and it's from a different group. I have nothing to do with them, but they're very good, and they 3D print light sheet. So we have a 3D, they give you all the information, and you can 3D print all the mountings. Then you have some cheap optics, and you can do some experiments with that system, definitely. Now, can you obtain the very same results? That I don't know. Probably if you have good optics, at the end of the day, what you need is a good camera, good objective, and a lot of patience, and a few other bits. But yes, I think yeah, we can think about it. I wouldn't say it's impossible. I'm sorry, I know I speak a lot. I can answer very quickly. I'll try.
Now, for your 3D images, do you move the images along an axis, or do you rotate in the plane?
Move along one axis. You can also rotate, though. You can. And also, sorry. But yeah, there are algorithms. There are some methods. Actually, my boss used to do that, where you can do that. You don't have to, but you can do that. There are algorithms where you can have rotation and translation to optimize the multiple views and the 3D. So now I don't have time for my next talk. What's the time? No, what's the time?
It's 11:30, you have 15 minutes delay.
Okay, so how much I have? But 45. Okay. So I will not go through the whole thing because otherwise there is not enough time. And so the idea was to give you the first. The talk that I just gave you was to hopefully excite you. I don't know. And now we go back to the basics. I will try to do this a little bit quickly. Well, not too quickly. Worst case scenario, I will finish next week. So let's see what we can do. But you can stop me anytime. So I've shown you light sheet fluorescence microscopy. That's an advanced technique for doing microscopy. Let's go back to the basics. This is the standard microscope that you might have used in the past. Okay? We've already seen how it works. I told you yesterday. Basically, in the case of a standard microscope, we acquire images by sending the light to our sample, okay, through an objective. And the light arrives to the sample. The sample can be either marked in a fluorescent manner or not. But some light will go back through the objective and then through a tube lens. And then there is a detection system. That can be your eye, or it can be a camera, okay? So the standard microscope is very simple. This is more or less the idea. But when you actually look into a microscope, it's not that simple. There are many optical components involved. today I would like just to focus on very few components of the standard microscope, of any microscope, because these concepts will apply also to all the other things I'm going to tell you. The first thing is the objective lens. This is one of the most important things. Also, if you want to build a Lego light sheet, you need to have a decent objective. This can be cheap, but sometimes it's the most expensive part of your system, okay? So when you have an objective, like this one, for example, the first thing you are interested in is the magnification of the objective. That tells you how big, how strong the magnification is, how strong is basically how much you are enlarging the sample, okay? The magnification limits, though, your field of view, because the higher the magnification, the smaller the field of view that you're going to look at. So if you want to look at a full zebrafish, you cannot use a high magnification objective, for example, because then you will only see the eye, for example. Then we have another thing that characterizes our objectives, which is the numerical aperture. I've mentioned this multiple times. I think that we've talked about numerical aperture already. Basically, the numerical aperture tells you how much light an objective can get, okay? So the more light, the best, because your image will be crisper and it will be more contrasted. So the numerical aperture is the other thing that you have to look for. Then another thing that is important is the working distance. So the distance between the objective and your sample. If your sample is big, you need space to put the sample under the microscope, okay? Usually this working distance is small for high magnification objectives and is large for low magnification objectives. And then another parameter that is quite important is the parfocal distance, which is the overall length of objective plus working distance. This is needed if you need to make sure that all the components will fit mechanically in your system. So this is an objective, is the way you see it, but inside it's very complicated. You can think of this as a single lens, but in fact it's really not. There are plenty of lenses inside an objective. It's a very complex object, okay? So, and all these lenses, they are there for a reason. So the numerical aperture, we said it's the cone of light, basically, that you can get with your imaging system, with your objective. The numerical aperture depends on this angle, okay? It's the angle of acceptance of your optical system and the refractive index, n, okay? So when you consider the numerical aperture of an object, you always have to take into consideration the medium that you're going to use your objective with, okay? In general, a lens that is a low magnification, like a 4x lens, has a small cone of light, because small magnification means long focal length, and it means that your field of view will be large, and the numerical aperture is usually small. In this case, for example, is 0.2. But a 100x objective instead has a small focal length because it focuses the light and gets the light from a very small area, so the field of view is small. And the numerical aperture is commonly high, okay? It's very high. So the fact that there is a dependency on the refracting index is due to the fact that the rays behave differently. The rays of light behaves differently in different media. So if your objective is a water immersion objective and you try to use it with glass that has an index of refraction that is different compared to the one of water, your objective is not going to work properly, okay? Because the rays deflect in a different manner from the way they were supposed to be when they have optimized the objective. And this objective, for example, has been cut in half, not by me. And here we can see all these lenses. So why do you think we have all these lenses inside a microscope? objective? Do you have any idea at all? Well, of course, it's because we need to magnify a lot, but also because we need to correct for aberrations, okay? So we have a problem when we have, for example, a sample with multiple colors. You know that different wavelengths focus in different points, okay? So if your lens or your object is not corrected for chromatic aberration, okay, you will have different images focusing in different points depending on the color of the light that you are considering. So objectives have all those doublets and triplets, all those lenses inside, because in this way they can correct for different types of aberrations. The main one is chromatic aberration, different colors. And of course, the more they correct for this chromatic aberration, and the more they are expensive, okay? But of course, the better they are. And in general, if we consider objective with increasing magnification, the numerical aperture increases, and the numerical aperture also increases with chromatic correction. Some of the best objectives have a very high magnification and a high numerical aperture. The high numerical aperture can reach even 1.45. If the numerical aperture is beyond 1, and the numerical aperture is the index of refraction multiplied by a sinus of an angle, sinus cannot be beyond 1, then it means that the index of refraction is not the one of water, it's higher, and the objective needs to be used, it's not the one of air. And the objective needs to be used either with water or with oil or glycerol or other media. But in general, high magnification means higher NA, and correction for chromatic aberration means also increase in NA, or numerical aperture. Another thing to keep in mind is that if you increase the magnification and you increase the numerical aperture, your working distance will become smaller and smaller. So you cannot fit big samples under a very high magnification objective, okay? There are some objectives that have high magnification, have high numerical aperture, and have a decently long working distance. If you see one of those, those objectives are worth probably 20K or more, okay? They are very expensive objectives. There are very few, they are very expensive. 20K only for the objective, because it's very difficult to obtain long working distance with high NA at high magnification. So let's go again to another concept that I'd like to stress, and that will be better stressed by Professor Pereira, and we already discussed this a bit yesterday, which is, again, the resolution of the system. So why is the numerical aperture of an objective or of a system important? Because the higher the numerical aperture, the better will be the resolution of your system. What's resolution? Well, there are different ways to, let's say, define resolution, but one way is the minimum resolvable separation of 2 points. Okay? If I have 2 points, the resolution is the minimum distance I need to tell them apart. Or another way is to look at the diameter of the central disk in a PSF. What's the PSF? The PSF is the system response function, is the instrument response function. So let's take a dot, okay? This is like a delta, a Dirac delta, okay? For example, a nanobead. This is something that is extremely small, okay? It's the only thing you have in your field of view. Your system will not be able to see something that is nanometric, for example, because what will give you is something like this, a dot that is larger. And how large is this dot? Well, it depends on the resolution of your system. This is how your system will respond to a Dirac, a delta Dirac. This is the same image that we have here, but in this case, we have enhanced the intensity, okay? If you enhance the intensity, you can see that there are the rings. This is an airy disk, okay? These are the airy rings. And to tell two things apart, basically, the minimum distance is the diameter of this dot. Professor Pereira will tell you everything about this, so I don't have to, okay? I'm not going to do it because I'm sure she will do better. But the idea is that this diameter is your limit. You cannot see things that are smaller than that. That's your minimum dimension of things you can resolve. And it's equal to 0.6 lambda, so the wavelength that you're looking at, divided by the numerical aperture. So if the numerical aperture is large, your diffraction limit is small. So you see things in a crisper way, okay? Or you can also, for example, decrease the wavelength that you're looking at, but that's not always possible. So let's see. This is an image that has been taken with an objective that has an NA, numerical aperture, of 0.2. So let's see if we increase the numerical aperture, 0.75, that's what you get. Of course, here we have enhanced the intensity just for this, the purposes of showing you. But you can see that this thing that might look like just a single blob, actually, if you increase the NA, you start to see, okay, maybe here there is a ball, that's another ball, that's another ball. These are maybe things that are different. They are all single objects in my field of view. You can also see the rings. The rings are very annoying. I don't like rings. I don't like rings, okay? But if we increase even further with a numerical aperture of 1.2, you can see there are many more than we had expected here. Yeah, I would never have guessed that there were these two, for example, you know? And not even with this numerical aperture. So look, with the numerical aperture going up, this is 1.2, probably this was a water immersion objective, okay? In this case, you can tell different objects apart, okay? So that's what happens when you increase the numerical aperture. All right. Actually, what happens when you have two things, that's also what I've shown you yesterday. So if you have two objects there, they need to be at least d, or 0.6 by lambda divided by the NA distance, at a distance of d, okay? At a distance of one airy disk, basically, okay? If they're too close, they might confuse them with a stripe, okay? And of course, okay, we can also say something about the contrast that we have in between the two beats, but it's not important. I just want to mention that that's not the only way, honestly, that you might find the definition of diffraction, or sorry, of resolution. Actually, there are different definitions, all slightly different. Like, for example, the one I have shown you is the Rayleigh limit of diffraction, and that gives you the resolution of the system with this definition of 0.61 by lambda divided by NA, and it is the dimension of the airy disk, the diameter of the airy disk. Abbe defined the diffraction limit in a different way as basically the 0.5 by lambda divided by NA. So in his opinion, you can still, for example, distinguish between two objects even in this situation, which I believe it's actually true. So 0.5 by lambda divided by NA. And the Sparrow limit instead basically tells you that if you have two objects that are close enough to have a plateau here in between, then you can still tell them apart. So he defined the minimum resolvable separation as 0.47 by lambda divided by NA. But you see, these different definitions are more or less, okay, they're all very similar. But you might find different definitions of the resolution criteria. Anyway, that's not everything. There is another thing that we need to keep in mind.
when we take an image? We take an image with a camera, which is a digital camera. We don't use any more analogic camera. Unfortunately, I have a collection at home. I like collecting very old cameras, but I don't use them for scientific purposes. The thing is, okay, let's even say that we are able to distinguish the two dots, but then if we have a camera that has pixels that are this big, well, we don't see anything, because both dots will end up in the same pixel. So what do we have to consider when we do imaging? We have to also consider the dimension of the pixels of our camera. In fact, we can consider our two dots as a continuous function. But to digitally represent this continuous function, okay, we have to follow the Nyquist theorem, okay, the Nyquist sampling theorem. And we have to sample it at twice the frequency contained in the continuous function that we want to digitalize, okay? So what does it mean? It means that if our resolution limit is 0.6 lambda and divided by NA, our pixels need to be at least half of this quantity. So 0.3 lambda divided by NA. The pixel of the camera needs to be smaller than the resolution limit. Okay, it's very small then, but okay, it's not really the dimension of the resolution limit, is the dimension of the image that I'm seeing on the sensor. I'll try to be more clear. So let's take this camera under X, well, it doesn't matter, but this camera, it's the same camera, and the third one is a different camera. And these two cameras that are the same one have a pixel size of 16 micrometers. Okay. And then we use, to look at our dots, objectives with an NA of 1.4. And in this case, a 60x magnification, while here we have a 1.4 NA and a 100x magnification. So what happens? The resolution is the same, but the dimension of the object in my image plane on the detector is going to be different, because in one case I have magnified it more. So the diffraction spot on the camera, when I see it, it's going to be larger if I'm using a higher magnification objective. This means that in this case, in the case of the 60x objective, the dimension of the dots that I will see on the detector will be 12.5 micrometers. Okay, 12.5 micrometers. But if my pixel size is 16 micrometers, then this means that I am not complying with the Nyquist criterion, because the pixel is too large for my diffraction limit. So what am I doing? I'm wasting time because I'm not sampling my image in a proper manner. Okay? And then what about this case? So here we have that with the 100x objective, the diffraction spot is going to be 20 micrometers, so it's larger, with a 16 micrometers pixel size. Okay, this is better. The pixel at least is smaller than the dimension of the spot, so I can sample it properly. It's not properly, better, but still not good, because we said it needs to be half. Okay, so another option is to use the 60x objective, 1.4 NA, so like the first one. So again, we will have a dimension of the spot on the camera that is 12.5 micrometers, but we have to change camera. Otherwise, we are wasting our resolution. We are losing time. With this other camera, this Andor Zyla, the pixel size is 6.5 micrometers. So 6.5 micrometers, it's basically half the dimension of the spot on the camera. So with this combination of objective and camera, we can sample properly our dots. Okay? So we are not wasting money on a stupidly good objective, but we have to invest on a camera with smaller pixel size. Okay. The other thing I want to, how long is it? 20 minutes. So the other thing is, I want to stress again this concept of the axial resolution. Okay, so this is in XY. So you look at something, just a picture. This is what you get. It's the resolution is the PSF that you have in your plane. But in microscopy, we are interested also in the Z direction, the orthogonal direction, okay? So the orthogonal direction is this one. So you see, it's an elongated thingy. So let's put it like this. This is the PSF in XY, but it's actually an ellipsoid, okay? It's something that is more elongated in this direction. So here we have projected it along the other side, okay? So this is like a lateral projection. So you see, this might look nice, but actually if we enhance the intensity, you see that there are these two cones here, one here and one there, that are not as pretty. So there are ways to improve in the axial resolution, and I will show you maybe later or next time. But the idea here is that this is the real shape of your axial PSF, okay? And we can describe the shape by saying that the resolution in Z, in the axial direction, is 2 times the refraction index multiplied by lambda divided by the square of the numerical aperture. So an objective with a high NA has a very, very much better axial resolution compared to one that has a low NA. Okay, so the most of the improvement is actually in the axial direction. So with an objective that has a high NA, you can do also, for example, better sectioning if you are doing confocal microscopy. Okay. And what I wanted to show here, yes, it's what happens when you change, in fact, the NA. So in this case, we have a NA of 1, and here we have an NA of 1.4. And you see that with an NA that is higher, we have a much nicer, a more confined PSF in the axial direction compared to what happens when you have a lower NA objective. Okay. The last concept that I want to touch is the depth of field. All these things, you can also apply these things when you take pictures with a good camera. Okay. So this is not only microscopy, it's imaging in general. So depth of field, it's another concept. I don't think we mentioned it already. But basically, it's the depth of field is for how long your object looks in focus. Okay. Basically, it means that if we have a high aperture, only few things will be in focus. Only what is close to the focal plane of your objective will actually be in focus, and what is far from your focal plane is going to be out of focus. If you want to have if you want to have things that are all in focus for a longer distance, you need to basically have a smaller aperture, and this will improve your depth of field. In this case, the depth of field is longer because all these objects are in focus. In this case, instead, the depth of field is shorter because these objects are out of focus already. Okay, so if I have an objective that has a very short depth of field, it means that if my sample is thick, I will have a lot of stuff that is going to be out of focus, okay? So the depth of field, again, depends on the numerical aperture. The depth of field, again, is dependent on the index of refraction, the wavelength of your, that you are observing, and it's inversely proportional to the numerical aperture of your system. So the higher the numerical aperture, the shorter the depth of field. Why? Because the PSF is smaller, okay? Because the PSF is smaller, so what is in focus stays in focus for less space. Okay, then I don't want to enter into the details of the rest, but I think that what I want to say is, how long do I have? May I ask? Okay, I just don't want to, I want you to go eat at a certain point. So, so the next part of what I would like to show you is going to be different methods of light microscopy. Okay, starting, I don't want to go through the bright field again, and maybe I can even skip the dark field. What I want to show you is why we use fluorescence markers, and then we will go through some of the best methods in microscopy that are currently being used to look at fluorescent samples, with a special focus on some super resolution techniques. Okay? So just quickly, I want to first of all mention the fact that, okay, I told you, with the bright field microscope, we look at cells. So this is a cell. It's the one I showed you yesterday already. But cells usually are quite transparent. So how do we see them? We need something like a contrasting agent. Okay, there are different ways of having a contrast agent. It could even just be the index of refraction of the cell itself if you're doing a phase contrast imaging. But another way that is very widely used in biology is to put a stain, to color your samples, okay? There are different types of stains that you can use. Some stains, basically, they really color your sample. They mix it blue, red, or other colors, okay? And different stains, they bind more easily with specific tissues, for example, okay? So, for example, alizarin red binds to bones, alkaline blue binds to cartilage, and so by staining, by putting this staining in your samples, you can get contrast between different types of tissues, for example, hematoxylin is a stain that you can put on your sample to see the nuclei, because it colors the nuclei of your cells in blue. But then eosin instead colors red blood cells in red, so that you can see them better. You can distinguish between nuclei of some cells from red blood cells, or there are other stains. For example, orsin stains elastin fibers, okay, so muscles. So if you want to look at muscles, you can put eosin, and you will see only muscles. There are many different types of stains. So they really color your sample will be stained. And you can look at these samples just with transmitted light. You just shine some light from a lamp, and you will see the colors with your eyes even. Okay, you don't even need a camera. Then, of course, if you need to collect the data, you need the camera. But okay, so to do this type of imaging, you can use a colored camera. But sometimes biologists want to be very specific. They want to be specific even to single molecules. Okay, that's why we use fluorescence, because fluorescence can be highly specific. It gives you specificity. Okay? We have dyes that bind specifically to some molecules that are in your samples. In this case, we are looking at some cells that were stained with probably this was nunc blue for the nuclei, which are here shown in blue, and the actin filaments, the cytoskeleton of the cells is shown here in red because it was stained with a molecule that went on just on the actin fibers attached to that, and that gave us the opportunity to look at the actin fibers. These actin fibers that are shown here in red, they are like strings, okay? You would never see them in something in this type of cell. You don't see. Yeah, okay, this is the nucleus. You could see it also without the fluorescent staining. But here, you cannot see the fibers. Well, you can do that with fluorescence, okay? They become very obvious. And then you can also do the same with tissues, okay? And specifically target with different colors, different tissues, okay? To be very selective to different types of cells in your tissue. And then you can also use fluorescence to see if your cells are dead or alive, for example. So there are some markers that are biomarkers that they tell you they bind to the DNA, for example, of your cell, only if the cell is dead, okay? Or if it is stressed, okay? So you can do some kind of live imaging that tells you something about the physiology of your sample. So here, these red cells, they were not, these cells are basically, they have absorbed the PI, the propidium iodide, which is a red marker, which is a red fluorescent marker, because they are dying. The others, instead, the green ones, they have absorbed only calcine. Calcine is a marker for live cells, healthy cells. So if we were looking at these cells without fluorescence, they would all look the same. But thanks to these fluorescent markers, we can see different cell conditions, okay? So this is why we use fluorescence, to be sensitive to something that you cannot see with transmitted light. And our microscope, the one that I've shown you earlier, that I've shown you yesterday many times, the standard one, basically just needs to be modified just a little bit by adding a lamp, like a mercury lamp, okay, so not an halogen lamp. Halogen lamp, they emit with a very flat, quite a flat spectrum. But for example, mercury lamp or xenon lamps, they have peaks, like lasers, okay? In fact, you can also use a laser. So you want a lamp that has lines of emission that are very, very thin. Like a laser, you can use a laser, in fact. Nowadays, we are using more and more LEDs as well. But if you add this type of lamp with very peaked lines, you can selectively excite the fluorescence of the dyes that you put in your sample. Of course, you need a filter, if you're using a lamp, to select only the bands, the spectral bands of your interest. And then you need a filter for the emission to block the light that comes from your lamp, okay? Otherwise, you would be blinded by your lamp, okay? So it's just an add-on. It's nothing that crazy. But I think you have understood. I really like 3D samples, okay? So let's see briefly again how confocal microscopy works. But because I've already shown you yesterday, now I'm going to ask you who remembers how the confocal microscope works. If you don't answer, I will point my finger at one of you, like I do with my students. So who knows? Who remembers? Who remembers? So the confocal microscope has one peculiarity. You need something to reject the out-of-focus light that comes from places that are out of focus. What is that? Do you remember? Anyone that remembers? The people are like, oh, don't look at me. Okay, I'll tell you, I'll remind you. That's why I put this slide. So we put a pinhole. So the idea is to go from an image like this, okay, that is fuzzy, to an image that is crisper, like this one, where you can distinguish between cells here. So here, for example, it's quite fuzzy, it's blurred. We want to be able to distinguish between cells. And to do that, what we do is we put here a pinhole. The pinhole is a hole. It's just a hole that rejects the out of focus light. Only the light that arrives from a specific spot goes through the pinhole. So we have a point source. We focus in one point our light. The light is collected by the objective lens and is sent to the PMT. So we have a photodiode, let's say, okay, just not a camera. In front of it, there is a pinhole. And this point is conjugated with the pinhole. So it goes through it. But what is out of focus, like here, doesn't go through. It doesn't go through. So it's rejected. So we can select only the things that are at the very focal plane in this manner. Okay? And then we have to move the sample, the beam. Okay, because I told you, with just one point, you don't do much. You need to scan your point. You need to do this, okay? Very quickly, in overall, the whole field of view. So here I have, there is a video. Oh, no, it didn't work. Can you maybe press this video, please? The top, yeah, this one. Yes. So you see, that's the idea. So you see that, okay, the beam moves, and while it moves, it creates an image. Okay? So you need to move your beam. We call it, we say that we have to raster scan the beam, and you synchronize it with your collection electronics, and you reconstruct an image in this way. You do that many, many times, because you are not very efficient with the confocal microscope. The pinhole is actually rejecting a lot of light. So how do you do that? You do that with mirrors and lenses. In fact, remember, when you have a beam and you have a mirror, the mirror reflects the light, of course. And if you rotate the mirror, you can have an angular displacement. And if you position a lens afterwards, you translate the angular displacement into spatial displacement. So an angular displacement becomes translation in the plane of the lens. Okay? The lens has to be positioned at its focal length from the mirror, and then at the focal length on the other side, we have perfect translation of the beam. Of course, if we want to scan the beam throughout our image quickly, we need to use galvanometric mirrors that are mirrors that move very fast continuously. So we sweep our beam. And this concept is used in many, many different types of microscopes. So it's in the two-photon microscope, and all scanning microscopes work like this. So we have our galvanometric mirror. We have the incoming laser, galvanometric mirror. The galvanometric mirror creates an angular displacement, which is translated into a translation by the first lens that we call scan lens. And then the focal plane of the scan lens is taken by the second lens, which is called tube lens. And the tube lens, again, translates the translation into angular displacement. The angular displacement is pivoted on the back focal plane of the microscope objective, which acts, again, as a single lens. And indeed, on the focal plane of our microscope objective, we have translation. Angular displacement of the galvanometric mirror means translation of the beam. Okay? So this is the way we manage to move our beam through. I'm almost done, I promise. Then we have all food. But I wanted to mention this other thing. So we talked about, again, the PSF and so on. So what happens in confocal with the pinhole? We said that in the axial direction, we had those cones, those horrible cones that ruin your image. Well, Confocal microscopy gets rid of those cones through the pinhole, okay? So you reject those two cones that we saw earlier in the PSF. This is the axial PSF, okay? What happens to the lateral resolution, in your opinion? What happens to the lateral resolution in confocal microscopy, in your opinion? Who wants? I want at least one person to try to answer. It doesn't need to be the right answer. What do you think happens to the lateral resolution? Do you think it's going to improve, get worse? Who says it improves? Who says it gets worse? Okay, we have one hand. Who says it doesn't change? Oh, come on. I was hoping for all the hands being raised. So the lateral resolution doesn't change because the detection system is the same. So it's the same. It doesn't change. The only thing that changes is the axial resolution because you have this effect of getting rid of the out-of-focus light. But the lateral resolution, it's the same. It looks crisper, but the resolution is the same. Okay? And then if we move the sample through the focal plane of our confocal microscope, we can get many layers, many slices, and we can reconstruct the sample in 3D. So between these two images, this is a tissue. Between these two images, the only difference is that on the right, we have rejected the out-of-focus light, but the resolution, the lateral resolution is the same. It's the axial resolution that has changed. And of course, we can make 3Ds of our samples. This is just to see that we can do cool stuff. Okay? So that's the confocal. And when it rotates, you might have seen that you could see the vessels that were round, while in the wide field on the left, it was not possible to observe something like that. And I think we can conclude, because the two-photon microscopy I told you yesterday, I just want to maybe remind you, but then I will quickly conclude. Just to remind you, this is not the only way of improving your Z resolution. The other way is also to use nonlinear effects. We heard about nonlinear effects today. We also use nonlinear effects in microscopy. We can do second harmonic generation, third harmonic generation in our samples, use them as the active medium. Or we can do two-photon absorption. And in two-photon microscopy, you excite only at the very focal point of your objective, thanks to the fact that there is the point where you have the highest probability to have two-photon absorption. Hence, you don't need the pinhole. But as I was mentioning yesterday, sometimes you need to use a lot of power. But the good thing about this method is that because you use twice the wavelength, you have less absorption from tissues, from the water, so you can go more in depth. They've done a lot of neuroscience studies with two-photon microscopy because they managed to go really in depth, even in a live mouse. They use two-photon microscopy because the absorption from the water in the IR is lower. Okay, and come on, we have to go to eat. Right. We have to? We don't? Oh, okay, then I'll tell you this last one that is, sorry. I speak a lot, I know. The spinning disk, okay? So we want to go fast. The previous technique, 3D, but come on, you have to move, you have to scan, it takes time. If you want to look at very fast processes, we are talking about microsecond maybe. That's far too slow, okay? One way to go faster is to use the so-called spinning disk. So it's similar to a wide field, but there is a trick, okay? The trick is to use, actually I think this one is clearer, the trick is to use a rotating disc where you have micro lenses, very small lenses, okay, that focus your light through another disc that is synchronized with the first one, where there are holes, many holes. So you don't have one pinhole, like in confocal microscopy, you have thousands of holes. And you rotate them quickly, okay? So in this way, you have a technique that is somewhere in between confocal and wide field microscopy, okay? You can go faster because you have multiple foci here that are being sent to your sample, and you can detect them again through the same spinning disk, this one with the holes, and send the emitted light to a camera. So not anymore a photomultiplier where you have to use the scan lens and tube lens to do the whole raster scanning. Here with the spinning disk, you can use a camera to detect your signal when you basically excite the signal through these two Yokogawa disks that rotate. So this method is actually, I don't know why it's not as used. I mean, the people, of course, use it. There are a lot of commercial versions, but it's not as used as I would think. But this is actually a very good trade-off between spinning disk and between confocal microscopy and wide field microscopy. And this is one of, and also I think this is very clever. It's a very clever idea. And with this, I really conclude now. So I'll show you the next things next week. Okay.
We are a little late. Please, Alessia will be
yes.
2 weeks here. You can ask her at any time. We have time for only one question, because please.
Okay, thank you so much. That was a good presentation. Now, in fluorescence microscopy, when spoken about some dyes
yes.
that you are going to use for coloring the cell organelles. Can you give some of the specification of the dyes that you use?
Okay.
Just to make sure that the cell organelles, they don't get destroyed or they don't get tarnished during the setup.
Okay, so if I correctly understood, you're asking me details about the dyes that I use. Is that correct? Okay, so the dyes that I use, they are always specific to the experiment that I have to perform. So most of them are actually dyes that you can find on, you can buy. Okay, so there is a big market on the dyes that you can buy, and they're very standard dyes. Actually, you want the dyes to be very standard, and so that your results are reproducible also by other people. And there are really, it's difficult for me to say, to give you the specs of the dyes, because there are really hundreds. So it's, but there are dyes that are specific, for example, not only for specific cellular compartments, but even for specific ions or molecules that are present in your cell. Okay, so for example, when I've shown the plants, in that case, the plants, I said they were fluorescent. That's different from, for example, when you put a dye, because that fluorescent was coming from the plant itself that had a genetically encoded dye that was placed there through genetic engineering by the biologist. So then that is something different. In that case, the biologist has developed its own dyes that are expressed directly by the plant. And in that case, it's quite interesting the fact that the cells, when they reproduce, they all have the same fluorescent dye incorporated already because it's intrinsic in their DNA. While if I stain my cells, for example, the cells will lose the dye after a while because when they split, when the cells split, they halve the concentration of the dye that they have, so they become less and less fluorescent. And another thing that you need to consider is that when you do imaging, you are exciting your fluorophores a lot, okay? You have to use the least amount of power to not overexcite the fluorophores, because if you overexcite the fluorophores, they bleach. So they just become non-fluorescent. There are some dyes, though, that are more resilient. They are more resistant to light. So you see, in different experimental conditions, you have to use different dyes, and that's very specific on the type of experiment that you want to do. So that's it's a very long reply that I have to. Sure. Sure.
One question from online says, what type of camera do you use for your fluorescence images?
Yes. So personally, for my, so for light sheet fluorescence microscopy, we commonly use an Hamamatsu Flash 4. It's an Orca Flash 4. The camera, I didn't say, I didn't tell you this. So the camera costs, I will give you some prices. The camera is very expensive. So I told you the objective is expensive. The other expensive part is the camera. The Flash 4, the Hamamatsu Flash 4 that we use, it's a CMOS camera. And it has a rolling shutter. I mean, it's a very nice camera. When we bought the first one 10 years ago, I think it was 15K. Okay, so 15,000 euros. Now the price has gone lower a little bit, maybe 10,000 euros. But then, of course, in these 10 years, things have improved. So the last camera that we have bought is again an Hamamatsu, but it is a fusion with a quantum efficiency that is much higher, which is high, not much higher, but it is higher than the Orca Flash 4. It's still a CMOS, so in general we use CMOS camera because they are faster, and we try to have cameras that can go faster. So when I say fast, I mean at least 100 hertz. For the Planck experiments, I use another camera, which is an Andor Neo. The Andor Neo has a very big sensor. The sensor is huge. It has 2,500 by 2,600 pixels, something like that. Now I don't remember. It has a very good quantum efficiency, and that camera has an internal memory, for example, and that camera can go to 1 kilohertz, so it's very fast. And we are now considering buying even faster cameras if we can budget on the number of photons. So the choice of the camera always depends, again, on the type of experiment that one has to do, to perform. If you want to go for fast camera, usually they are not the best in terms of quantum efficiency. If you want high quantum efficiency, usually the camera is lower. So it depends on what you want to, let's say, prioritize.
Okay. Let's we thank again Alessia for the
Thank you very much.
And we move to the next one. Our next speaker is Mamadou Diop.
There is no food.
He's coming from the Western University in Ontario, Canada, and he will present near-infrared tissue spectroscopy focused on non-invasive point-of-care neuromonitoring. But I want to highlight something about our speaker. He's originally from Senegal. In my opinion, it's a very good example for you students of very hard work. He's now a very prestigious researcher around the world, and as you please interact with him, because he can give you a very good example of how he could reach this level, and also, in my opinion, you can do, working very hard. Then, Mamadou, the floor is yours.
And as you guys can see here, Senegal is the most western part of Africa, right in front of America, and that has historical implications. So I went to this university, which is in Dakar, Senegal. It's called University Cheikh Anta Diop. Cheikh Anta Diop was a physicist, an anthropologist, and has the same name as me. His name is Cheikh Anta Diop. And the university is called Cheikh Anta Diop. There is an institute there that does research in African heritage and history. He was an Egyptologist as well. So this is one of the one of the building in campus. This is where the student dorms are, and I lived in this student dorm for 4 years. And this is a library, and this is one of our crowded amphitheaters. Ours was less crowded than this, but this is from the Faculty of Law. So now so I did my undergraduate in the University of Dakar. My undergrad was in physics. So I did a dual degree, one in physics and one in chemistry. And that you will see that that will transfer in my career. And when I finished my undergrad, I went to teacher's college. In the meantime, I was doing my master's. So I have a teaching degree and I have a master's in physics. And after that, so those are the degrees that I have from University Cheikh Anta Diop. And from there, I went to Quebec City parce que je parle français, because I speak French. So it was obvious, it was easier for me to move to Quebec City, to Laval University, where I did my PhD with this guy, Professor Roger Lessard, who was an SPIE fellow, and some of you guys may know him. He passed away now. And this was our campus. Okay. So this was our campus here. And I did my PhD on colloidal photonic crystals. Some of this. So on colloidal photonic crystal, and this is the Center for Optics and Lasers and Photonics at COPL at Laval. That's where I did my PhD. And after I finished my PhD, I went to I literally drove from Quebec City to Ottawa with one of my friends to go to the National Research Council of Canada, where I landed a position as a postdoc. So I spent 2 years there, and while I was there, I discovered medical physics, and it was an eureka moment for me. After 2 years of postdoc, I decided to stop and completely change field. And so this gentleman here was my former PhD, postdoctoral supervisor, a very nice guy, gentleman. He still lives in Ottawa, and his house. This is the Ottawa River here, and in his backyard. So he's now retired and enjoying life. So from Ottawa, I literally drove to London, Ontario. So in London, here, so this Toronto is around here. This is London. Detroit is around here. And you see, we live in the region of the Great Lakes. I went to London, Ontario, where I'm still right now. And I did a 3-year postdoc there. At that time, I completely changed field, and I started working on biomedical optics. So everything I'm going to be talking today about is going to be the work that I have been doing in London. So just, I'm going to give you an overview of what I'm going to be talking about. First, I'm going to start with light-tissue interaction. Then I'm going to talk about functional near-infrared spectroscopy. And I'm going to introduce to you how do you use diffuse correlation spectroscopy, which is another optical spectroscopy technique to monitor cerebral perfusion. And I will end with a technique for non-invasive continuous monitoring of cerebral metabolism and blood flow at the point of care. I'm not going to be able to cover all of this in 1 hour. I'm going to go through the lecture, and when after 45 minutes, 50 minutes, I'm going to stop. We'll have questions, and then I will continue on Monday. Light interaction with biological tissue. So this is a simulation of light, so you can, the interaction with skin. As you can see here, when light propagates in, like my laser pointer, it goes in a straight line. When the light propagates in air, okay? However, when the light hits the tissue, you see now the path is now tortuous. And this is because of light scattering. And Alicia mentioned yesterday that it's because of the refractive index mismatch within the tissue that you have this light scattering. So tissue is a very strong scatter of light. That's why it's very hard to generate high-resolution images of biological tissue. So light paths in tissue are not straight line because of light scattering. I've noticed that the front has been changed completely, but it's fine. The other observation that can come from here is that in this simulation, this was a Monte Carlo simulation of light propagation in tissue, the same number of photon, red and blue photon, was launched into the tissue. And what do you observe here? You observe that you have more red rays inside the tissue than blue rays. That's because tissue absorbs more blue light than red light. And I like to show this to my students. So you can see this is white light, and that's red, green, and blue, right? I put my finger on, what do you see? What color do you see? Why? Any answer? Why? Why do you see red? Why so I injected red, green, and blue into my finger, but I only see red. Yes, yes, yeah? Yes, attenuation of the tissue. So the tissue absorbs the green and the blue, and the red propagate through it. You see that? And we take advantage of that. When we're going to do, you're going to see in my next slide, when we're going to do tissue spectroscopy, we don't use green and blue because they're going to be absorbed by the tissue. And we're not going to detect anything. We use red and a little bit longer, which is near infrared. Okay? We're going to use red and near infrared light. And I have this illustration here where you see the blue is absorbed right into the first layers of tissue. The green propagates a little bit. With the red, the whole finger is glowing. And that's because in tissue, we have the two main light absorbers in tissue are blood and water. We are made of more than 75% water. We are just bags of water walking around, literally. So we are made of water and blood. Blood is the strongest light absorber in tissue. And these are the specific absorption coefficients, molar absorption coefficient. In blue here, we have the molar absorption coefficient of deoxyhemoglobin. Remember that. In red, there's a molar extension coefficient of oxyhemoglobin. And in green, I have the molar extension coefficient of water. It's a scale because water absorption is much weaker than the absorption of blood in this wavelength range. You can see here, I'm going from 600 nanometer to 1,000 nanometer. This is red to near infrared. And there is a reason for that. Besides these main strong absorbers, we have others, such as fat, which is this purple curve here. And we have this molecule here. I'm going to come back to this molecule either today or on Monday. This molecule is called CCO, is cytochrome C oxidase, and I will spell it out. And it's another very interesting molecules that is in the tissue, and we can use it to monitor oxidative metabolism. So what I'm going to do here is I'm going to show you now this window here. You see, from 700 nanometers to 900 nanometers, you can see that the absorption of these light absorbers is very low. It's kind of minimal. You still have these features. They still have these features, but the absorption is very low. And this window here is called the optical window. It's the range of wavelength where the main light absorbers in tissue have very low absorption, so tissue becomes transparent. Another important aspect is that light scattering decreases as 1 over lambda to the power of, let's say, 1.2, okay? So also, light scattering also decreases when the wavelength increases. So the combination of those two made that when I put this flashlight on my finger, you can see the red light. It goes through. So your eye is a very sensitive detector, actually. So if your eye can see it, now if I use detectors that are much more sensitive, such as PMT, photomultiplier tube, or CCD cameras, or single photon avalanche photodiode, which can measure single photons, they are single photon counting, you can imagine I can detect a lot of photons. Now, in near-infrared spectroscopy, we also call diffuse optics. We have 3 main techniques. We have continuous wave, where you have, which is like my laser, or the flashlight on my cell phone. The intensity is constant. The only thing you can measure is light attenuation. So if you put your light source here, and you put your detector here, this is the probability density of photon path. If you detect the photon here, okay, it's kind of a banana-shaped form. That's the probability, the most likely path of the photon you detect here if your light source is here. If you are in transmission mode, this is the probability density of photon travel. So this transmission mode, you can use it if you are imaging a finger, and we do use that. This is the reflectance mode. We use that when we are probing the brain, okay? Now, if I put my source here at S, and my detector is at D, and they are separated by rho, which is the source detector distance here, with a continuous wave light source, which is like my laser pointer, I can only measure attenuation. Now, if the light source is modulated, I can measure both attenuation and phase shift. This is called frequency domain mirrors. Now, if I use a single pulse of light, now what I'm going to detect here is the distribution of the photon path inside the tissue, okay? Now, all these are the 3 main techniques that are used. My lab work on continuous wave nears and time resolved. We don't do frequency domain, okay? And I have my own reason. If you want to discuss it with me, I can discuss it. So when you go from continuous wave to time resolved, you have increased cost and complexity, okay? But you have an increased information content. Somebody said earlier, I think it's Annie, I said, there is no free lunch. Obviously, yes, there is no free lunch. You have more information content, the system is going to be more complex and going to be costly. Now I'm going to focus on the simplest of the technique, continuous wave near-infrared spectroscopy. I will refer to it sometimes as CW. Oh well. Okay, so for now, let's focus on this side. When you have, this is chemistry 101. Here you have a light source that goes into a cuvette, and the cuvette has a light absorber, and the intensity is attenuated. Very simple. And you can use the Beer-Lambert law to describe this. This is chemistry 101. In tissue, it's a little bit more complicated. You know, because when you look at this is modeling the photon, the probability density function of the photon travel inside the tissue when your source is here and your detector here. And you can see it's not, this is the banana-shaped, the red region here is the banana-shaped region that I was mentioning. And you can see here, the light attenuation is a little bit more complicated. You have the first part here, which is your input intensity I naught. Mu A here is your absorption coefficient. L is the source detector distance. But you have this factor here. The source detector distance is multiplied by a factor. This factor is called differential path length factor. And this differential path length factor accounts for the increased light path due to scattering. But you also have this term G here, okay? So if I take just the log minus the log of this, and I have this expression, his G here, account for light attenuation due to scattering, okay? As I mentioned, light tissue is a strong light scatterer. Now let's look at this equation, see this optical density here, light attenuation. So if I come back here and I look at the optical density, it's a function of absorption and scattering. And if I do a Taylor expansion of this, here, I can get this equation here. So what happened is, in tissue, typically, things are static. We don't have a change in light scattering. Light scattering in tissue doesn't change much. And because of that, then I can simplify my equation here. I'm going to go from this equation to here because delta mu s prime is very small compared to delta mu a. So change in absorption is much larger than change in scattering. So this first term here of the Taylor expansion becomes dominant. And now this first derivative of my optical density with respect to the absorption coefficient here is called the differential optical path length, okay? And it's equal to the source detector distance times the differential path length factor here, dpf. And that's what I wrote here. If I now take this same equation and I bring it here, so I just put this same equation here. Now, if I now express this light attenuation as a function of wavelength, because I'm using multiple wavelengths, I'm not using a single wavelength. Optical attenuation is a function of wavelength, and that's what I express here. You can see the source detector distance doesn't depend on wavelength, obviously. The differential path length factor, dpf, is a function of wavelength. And the absorption coefficient, change in absorption coefficient. And you notice here I'm using CW, continuous wave. I can only measure light attenuation, okay? That's all I can measure. That's what I express here. So my light attenuation as a function of wavelength is equal to the source detector distance, this differential path length factor, which is a factor that you have that account for the increased light path inside the tissue due to scattering, and the absorption coefficient of the tissue. Now, I can now take this equation. It's very simple. I just divide the optical density because I measure this. I know the source detector distance, and I can estimate the differential path length factor. From there, I can estimate the attenuation, the change in light absorption in the tissue with respect to wavelength. Here, I know by definition, the attenuation is extension coefficient times concentration. And then change in attenuation is just due to change in concentration. And from there, so the epsilon here are the wavelength-dependent molar extension coefficient, and they're shown here for water and oxygenated and deoxygenated blood, okay? And now here, if I am doing now functional activation, okay? And functional activation is similar to when you have fMRI. Let's say that if I'm doing this, if I had a detector on here, on my head here, on this part of my head, this is the motor cortex, I will detect change in light attenuation because I'm activating my left motor cortex by doing my finger tapping here. So then I don't need to, because I know the water is not changing, so the change I have here is just due to hemoglobin. Okay, So I can use 2 wavelengths, and typically commercial near-infrared spectroscopy system, they only use 2 wavelengths. One that is tuned, this 800 nanometer here is called the isobasic point, because at this point, both oxygenated and deoxygenated blood have the same absorption. So what you do, you have a wavelength that is on the left-hand side, so shorter wavelength than your isobasic point and a longer wavelength. They typically use 750 nanometers, which is this wavelength here. This is the absorption peak of deoxyhemoglobin is 750 nanometers. And they use another wavelength here at around 830. And if you want to monitor total hemoglobin, you can use the 3rd wavelength. But typical commercial system use only 2 wavelengths. Again, so if you put your source here, your detector here, and I'm doing my finger tapping activation, this is what's going to happen. I'm going to see an increase in oxyhemoglobin and a decrease in deoxyhemoglobin. This change here, in the baseline here, you can see at the beginning I have nothing, so I'm here, I do nothing, and that's my baseline here. And when I start doing my finger tapping here, what's going to happen is I'm going to have an increase in oxyhemoglobin and a decrease in deoxyhemoglobin. And that's a signal that can be detected with near-infrared spectroscopy, okay? And you can also detect that using fMRI, using MRI. And I will show example where people have done an experiment where they compare fNIRS and fMRI, functional near-infrared spectroscopy and functional MRI. Why do we bother? Because we already have fMRI. Why do we bother using NIRS? There are multiple advantages of using functional near-infrared spectroscopy instead of fMRI. Like example here, you see this infant. If you want to study the brain under development in real environment, you cannot use MRI. Because in an MRI, you're laying down in a scanner, you have this cage sitting in your face, and they ask you to not move, okay? You do not move. If you move, the images are garbage. They develop algorithm to correct for movement artifacts, but you don't move. And it's noisy. Doing fMRI in toddlers is a nightmare. Some people have done it, but it's a nightmare. But you have to acclimate them, and they can only do very specific tasks. If you want to study brain development in the natural environment, fNIRS is the technique. And you can see this kid. He's wearing this helmet with different source detector, probing the whole brain, and it's mobile. If you want to study mother-baby interaction and what's activation of the brain, it's a technique to go. If you want to now study somebody exercising, what's happening to their brain, or when two people are interacting here, technique to go is fNIRS. So this is a reason why you have maybe already heard about NIRS or near-infrared or NIRS or fNIRS, because this is the fastest growing segment in our field of biomedical optics, because now we have a lot of neuroscientists, developmental scientists who came to our field and are now doing the bulk of this type of work. Actually, we have now a society called the fNIRS Society, and we have a conference in Birmingham in, I believe, in September. And at the beginning, when we started this conference, it was just people like us, engineers and physicists, sitting in the room and talking about technology. Now, more than 2/3 of the conference are from people who are now taking these tools and applying them and answering what matters, answering questions that can affect life of people. So in this example, this work was done by the group of Joe Colvert at Washington. And so this here, the person is standing, looking at a checkerboard, and they have the fNIRS system sitting on the back of the head to just monitor the visual cortex. This is it's called high density diffuse optical tomography, but it's just the same, just fancy name for fNIRS. And here, fMRI. So the same person. And you can see not only there is a very excellent spatial correspondence between the two, but when the checkerboard moves around, there is the part of the brain that is excited, okay? When you do the measurement using the fNIRS and when you use fMRI are exactly the same. And this is an example from one participant, and you have here an example for 5 participants. You can see on the top is the bold fMRI, and the bottom is the deoxyhemoglobin signal obtained from functional near-infrared spectroscopy. And the beauty of NIRS is that you have both oxyhemoglobin and deoxyhemoglobin. In fMRI, you only have deoxyhemoglobin because that's the compound that is paramagnetic. That's what you can detect. So using both oxy and deoxyhemoglobin provide more robustness in your measurement. The question that people always ask me, when I talk about using near-infrared light to probe the brain is they say, can it go through the skull? And they hit their head. Yes, the skull is hard, but near-infrared light can go through skull. When I put my finger on the flashlight, I have bones here, but you were able to see the red light, right? And in this example, this is a tissue mimicking phantom that have similar optical properties as light, as tissue, and there were a light bulb inside the skull, and you can see it here. The red light is coming out. Okay, well, because if you can see light coming out, that means that if you put light out, it will go inside. Okay, just illustration here. And people, this is just like an illustration, but people have done simulation to model how much the light will attenuate. Let's say that here, if you go to a depth of 3 centimeters below the surface, let's say that I put a light source here, and I go 3 centimeters inside, that's really going below the cerebral cortex, because an adult, the extracerebral layer, the scalp and skull of an adult head is about between 1 and 1.5 centimeters. So a 3 centimeter, which is 1.5 centimeter below within the brain, you still have about 1.5% of the light, of the photon that are surviving. And if you are doing single photon counting, that's tons of light. So yes, you can probe the brain by just putting optical fibers or LEDs on the scalp and putting another photodetector or another optical fiber 3 centimeters away. You will be able to probe the human brain. This is a study that was done by my group. So we had this helmet. So I have to make a disclosure here. So this helmet here was made by a company called Kernel, and they are in Los Angeles. I was a consultant for the company during the development of the helmet, but I have stopped any financial relationship with the company now. And the study I'm reporting here, the company were not involved in the design of the study, although we received one of their helmet for free. Okay? So what you have here is this helmet that the company made. And this helmet is a high-density fNIRS system that you can wear, and you can walk around. And inside of the helmet was populated with this module, this hexagon module. So you have a light source here, and you have 6 detectors around that. And because the modules are not far apart, you can also have light that come from one module to go to the other module. And because of this, you now crisscrossing the brain, and you can do very high density sampling of the brain. And in this example, because I don't do work on fNIRS, like the functional activation stuff. My lab is more interested in measuring physiological parameters, and because we are in a hospital and we work with patients, we work directly with patients. So I'm more interested in measuring physiological changes and situations that are similar to clinical scenarios. In this example here, so this study was done on healthy volunteer. And what we did is we put the FNIRS cap on the head of the participant, and the postdoc will come in and do a carotid compression. And this is called digital carotid compression. CC here stands for carotid compression. Does a, as you can see here, a 10-second, I believe, yes, a 10-second carotid compression and then a release. And then we measure, and we average that, and we look at that for the whole population. And what you can see, and we expect this, we have baseline, and we start the carotid compression, we have increase in deoxyhemoglobin, because in the ipsilateral side, in the contralateral side, we didn't see anything. It was a flat line, okay? But in the ipsilateral side, what we see is we have an increase in deoxyhemoglobin, because you're impeding the flow of blood to the brain. We have a decrease here in oxyhemoglobin, which is in red, and total hemoglobin decrease as well. This is expected. And this was a sanity check for us to see if the system is doing what it's supposed to do. The additional work we did is to map the entire head and see now, we take this device and we put it on patient undergoing shoulder surgery. And because when somebody is going under shoulder surgery, what happens often is that because they are sitting on the bench chair, they are unconscious, and so we put the helmet on their head, and what happens is they experience hypotension period. And this hypotension period can have negative effects on their brain, and that's why sometimes people will recover from the surgery, and because they're not operating on their brain, they're not operating on their heart, they're operating just on the shoulder, and they start to have cognitive decline. It's because they have extended period of desaturation, cerebral desaturation. And the objective of this study was, can we measure that? The paper was just published this week. I think this weekend, actually. I received the notification when I was flying here. So that's one of the applications. So you can take this helmet and put it on the head of a patient undergoing surgery, and you can monitor the brain. Now, as you have seen in this slide here, when you use continuous wave NIRS, CW NIRS, where the light intensity is constant, you can only measure light attenuation, okay? And because of that, you can only measure changes in your chromophore, changes in oxyhemoglobin, changes in deoxyhemoglobin, changes in water. But my lab is, we are a translational lab. We are interested in quantitative spectroscopy, quantitative measures. So if you have continuous wave NIRS, how can you make it now quantitative? And in the next 10 minutes, I'm going to walk you through the process of how you can take continuous wave NIRS, which is just can only measure attenuation, and make it quantitative. So this paper is now a few years old. So basically what happened is, traditionally when we do spectroscopy, what we have here is a halogen lamp, and we couple the halogen lamp to an optical fiber, and the optical fiber, this is a tissue mimicking phantom. It could be like somebody's head, right? And when the light is reflected from the tissue mimicking phantom, we collect it with another optical fiber, and we send it to this spectrometer. So this spectrometer here, it was not meant to be used for tissue spectroscopy, but you have to be, because we are an engineering lab, so what we do is we take this spectrometer that we bought from Ocean Optics, and we remove the slit in front of the optical fiber, because they put a narrow slit in front of the spectrometer. And we design the fibers here. We have round to linear. So the detection fiber is round here, which is this end, but the end that go to the spectrometer, we make it as the form of a slit. And we did our calculation. And what we found is that we can have this 215, and now we have continued the work. Now we can go to a little bit wider, actually. We can double the light throughput. And when we did this, what happened is we took an off-the-shelf spectrometer that costs about $12,000 US, and compared to typical spectrometers that would cost 3 times. The spectrometer we used to use for tissue spectroscopy used to cost 3 times, and we convert it. So that's why improved light collection. We do some algorithm at the back. Obviously, when your when your system is simple, you have to do a little bit of math in the back. And we denoise the signal, and we're able to use this very simple setup to now do quantitative spectroscopy, tissue spectroscopy. And how? Okay, let's go back to this figure here. These are the absorption, specific absorption coefficient of deoxyhemoglobin in blue, oxyhemoglobin, and water in black. If I take the spectral derivative, okay, if I take the spectral derivative of this curve, and I do it twice, not the first, but the second derivative of this curve, this is what I obtain. And I want you to pause here and think and pay really attention to this. So in blue here, what I have is the second spectral derivative of this blue curve. In red, dotted red, is the second spectral derivative of this red dotted curve here, which is the absorption coefficient of oxyhemoglobin. And in black, I have that of water. Why this is important? You can see that if I focus strictly in this range here, between 800 here and 850 nanometers, which is this region here, you see that the contribution of both of both oxyhemoglobin and deoxyhemoglobin is very small. So in this region between 700 and 800 nanometers, so the contribution of the main contributor here is water. If I isolate that window and I fit my data, the crosstalk between the concentration of water that I'm going to obtain and the concentration of these isochromos are going to be minimum. So I'm using this window, like range, spectral range specific fitting approach to isolate the water peak here. And now, if I come to this region here, once I know the water, once I do the fitting here, I can estimate the water concentration. And now I can come to this region between 750 and 800 nanometer, where I have, contribution of water and deoxy. But I fix the water concentration to the value I get earlier. And I'm going to go to that. I'm going to show you in the next slide. So I'm going to start with this. Thanks. So this is the attenuation we measure. Okay? I'm going to just skip. So this is the second derivative that I showed you. And you just fit it with a theoretical model, okay? A solution to the, for instance, the diffusion equation to a multi-layer system. This is the 700, 800 nanometer region I'm saying. So this blue curve here is an experimental curve. It's a measure that I acquired on an animal, on a piglet head. And you can see here, and red is the fit of the theoretical model that allows me to estimate my water concentration, and I have 85% water concentration. And once I get the water concentration, I fix it, and I fit this region here, the curve I fit in this region, to get only one parameters, to get the concentration of deoxyhemoglobin was 16 micromolar, or 13 micromolar here. And once I get these two, the reason why I do this is to avoid crosstalk, because if you don't do this, because you are only measure attenuation, it becomes an intractable problem. You will have lots of crosstalk. Now, once I get the water concentration and deoxyhemoglobin concentration, I go to the first derivative of my attenuation, and you see, and I fit the entire curve for the entire spectrum to estimate the oxyhemoglobin concentration. And by doing this, I eliminate crosstalk, and I can quantify all these different chromophores reliably. So, cytochrome C oxidase. Now that I have a broadband light source, I have estimated the concentration of water, deoxyhemoglobin, oxyhemoglobin. Now, I can go now to my attenuation and take my attenuation curve and estimate the concentration of cytochrome C, because cytochrome C has a very low signal, and when you look at its derivative, it's flat as well. So if I go to the spectral derivative, I will not be able to estimate it. So why cytochrome C? Cytochrome C oxidase is a enzyme that sits, so this is the mitochondria, and it sits in the inner membrane of the mitochondria. So this is the electron transport chain, and cytochrome C oxidase is complex 4. It's the last electron acceptor in the electron transport chain. And once it receives an electron, it passes the electron to this redox stage here, which is copper A. So copper A has 2 colors. When it's bound to an electron, it has different spectrum compared to when it passes the electron to the next redox stage, which is copper B. And we can measure this change in color of copper A. And once that electron is now passed to oxygen, and oxygen is now reduced to water. And each of these steps, there are these complex 1, 3, and 4 are pumping proton to the outer cell, to the inner membrane, and this inner membrane is using it to drive the ITP synthase, and that's this proton drives are the fuel that is used by this ITP synthase to work and to synthesize ATP. And you know that ATP is the main fuel for tissue. So by measuring now this change in color in copper A, we are basically monitoring the consumption, oxygen consumption in the tissue. So that's why cytochrome C oxidase is a very sensitive marker of oxidative metabolism, how tissue is metabolizing oxygen. So cytochrome C oxidase is necessary for oxidative metabolism. It drives ITP synthesis. It's very important. That's why if you see that the cytochrome C oxidase is stable, it's not changing, then you know that there is metabolic crisis. And it provides a direct measure of oxidative metabolism in tissue. I have 3 minutes. I can continue. So why is metabolism and flow important? I'm going to actually stop with this slide. So this is a study that we did a few years ago. Sorry? 15 minutes? Okay, if people are not tired, yes, it would be great. So I will start timing myself. So so why is flow and metabolism important? Flow, we can understand it because blood flow is what brings oxygen and nutrients to the tissue, to the living tissue, and also take the byproduct of metabolism away. This study, we did this study a few years ago, was done by Joel Cooper, who's now a medical doctor. He was an MD student with us. What we're showing here is this is a relative change in flow. So the baseline is 1, okay? And when you are here, you only have 40% of the blood, initial blood. And what we are showing here is the metabolism. And what we were doing is this experiment was done on pigs. We put the probe on the head, and there were 2 medical doctors and Joel, and they were doing this clamping of the carotid arteries to monitor, to model, to mimic what happened if somebody is going under carotid endarterectomy, because that's a procedure. Some people, they would have plaques in their carotids. So the medical doctor would have to come and clamp the carotid arteries. So they rely on the collateral flows that come from the other side. So the other carotid arteries will perfuse this part of the brain, but because we have the circle of Willis, we evolved to have the circle of Willis, the blood will go into the other side and supply the other brain. And it's a very dangerous, you can imagine, it's a very dangerous procedure because if there is any plaque or any blockage, then you lose this redundancy that nature has built. So what you show here is that we have this physiological reserve. When blood flow decreases, metabolism remains almost the same up to a certain point here. It's around, when it drops to about 75, a little bit over 70% of the initial, if you have a drop of 30% of blood flow. And then you start to see now a linear dependence of metabolism on flow. And this region here is called a metabolic crisis. You don't want to be in this region. If you are in this region, that means that now the metabolism of your brain, of the brain, depends on the supply. Because if your usage only depends on supply, so you are supply limited. And that's what causes brain injury. Because why this is important? Because if the blood flow to the brain, in an adult, like if we did a measurement, if I had one of my devices here and I did a measurement on your brain and I measure your blood flow, it would be 50 milliliter of blood per 100 gram of tissue per minute, roughly. Very, very similar. Now, if the blood flow to the brain drops to 10 to 23 milliliter per 100 gram of tissue per minute, you have electric failure. The brain doesn't tolerate lack of oxygen. That's why if somebody knocks you here, you pass out. Because the brain tries to preserve itself, okay? Because when you are awake, you're listening to me. You're consuming a lot of energy. But that's why when somebody knocks you on your carotid artery, you pass out. Because you wanted to. And now it's between 10 and 15 milliliter of I call it unit of blood flow. Between 10 and 15 unit of blood flow, we have membrane failure. So it's extremely important to maintain a constant and continuous supply of blood to the brain. If not, you have brain injury very quickly. That's why if somebody has a stroke, well, the consequences are devastating. I can put a cuff on my hand for 5-10 minutes, and I'm going to be fine after I release the cuff. If somebody cut your carotid, the supply to the brain, to your brain, for 1 minute, you're dead. So it's very, very important, especially during clinical procedures where we know by fact that the supply of blood to the brain is compromised, can be compromised. In those situations, you have to monitor the brain. And unfortunately, right now, up to now, because now we have developed the tools, we did not have any technique that can monitor the brain, the blood flow and metabolism to the brain at the bedside, which is ridiculous. Why? Why on earth? Like the world has existed for so long. Why we were not able to monitor the brain, to monitor flow and metabolism at the bedside? People use EEG, but EEG is an indirect measure. Okay? It's better than nothing, but it's an indirect measure. Why metabolism? If the metabolic rate of oxygen, it's called CMR2, drops below 1.3 units per 100 milliliter per 100 gram, 100 milliliter of oxygen per 100 gram of tissue per minute, you have infraction. Okay? I'm going to stop there. So this is to tell you that monitoring the brain, monitoring flow and metabolism to the brain is critical. During my next lecture, I'm going to teach you how you can develop techniques that allows you to measure continuously absolute cerebral blood flow and absolute cerebral metabolic rate of oxygen at the bedside. Thank you.
Thank you for a nice presentation. Maybe we have time for questions. Please.
be back.
Yeah, thank you so much, Prof, for that presentation. Now, my question is in that instrument that you use, especially the helmet. And I want to ask this question: what is the duration? For how long is it supposed to be in that head? Like the duration, and also you've talked of three methods of. You've talked of the continuous wave, and also there was the other one, but not the frequency domain. Why?
Okay, great. So I'm going to start with the first question. The helmet, it was not very practical. And during our first study, the helmet could be on the patient for a couple of hours for the whole duration of the shoulder surgery. In my lab, we developed, and I will show example, a device that you can put on somebody's head for days, okay? It's not a helmet. It's just the device is there, and you have optical fiber that comes to it. The helmet has some design flaw. I was just a consultant, and they did not listen to me on things that I told them. But they have a second iteration of the device. I haven't seen the second iteration of the device. So the helmet was very heavy, and we would have a neck brace. So the patient would put them a neck brace to support the device. The device was more than 1 kilogram. So the helmet was heavy. Now, your second question was why we do not do frequency domain. As somebody who's trained in optics, I quickly realized when I moved to biomedical optics, and it was at a time when the lab I was doing my postdoc were considering going from continuous wave NIRS to a more advanced near-infrared spectroscopy, which was going to be either frequency domain or time domain. And I knew that in frequency domain, you measure you measuring phase and amplitude. And phase is inherently noisy. Anybody who does optics knows the phase is inherently noisy. And if you want to use that now to quantify your scattering coefficient, the precision in your measurement, in your scattering coefficient, measurement of your scattering coefficient would be challenging. And at the time, we were lucky that the lab was wealthy, has money, because time domain is a little bit more expensive than frequency domain. So I steer them to go into time domain, and that's what we do. We do time domain NIRS. We have all kind of time domain NIRS, and sometimes we combine with CW to calibrate the CW. Instead of using multiple wavelengths, just use 3 wavelengths. And you use 3 wavelengths, you place them, you choose them strategically. You can use the information that you get from the time domain now to calibrate the continuous wave so that you can have now, instead of having just 3 measurements, you have hundreds of measurements. Actually, the spectrum I showed was 200 nanometers, 650 to 850 nanometers. That was the reason.
More question, please.
Yes, right there, right here. David, probably.
Thank you so much for that informative presentation. Just a thought crosses my mind. For example, even now when we are listening to you, there are quite a number of activities that are happening in the brain. I mean, by virtue of the fact that I'm also flexing my eyes. So that is also controlled from the brain. Now, with your method, what is the kind of resolution that you're able to detect this kind of metabolism that is happening in the brain or activities happening in the brain? Do they have to be certain magnitude so that we can be able to detect them? Or to what extent are we able to detect what is happening in the brain in real time?
Yeah, so that's a great question. So what happened is, when you're right, when I'm talking right now, you're listening to me, your brain is activated. So the detection limit, so for oxy and deoxyhemoglobin, we are able to detect less than 1 micromolar, so which is very small. So even very tiny, because this activation, the activation change due to activation is very, very small. But these detectors are very sensitive. So yes, there is a limit, a minimum limit where you're going to be on the noise of your signal, but that depends on your baseline. Okay, if you're semi-stable, so if you are two standard deviation above the standard, if your signal, your change in signal is beyond 2 standard deviation of your baseline, then you can detect it. So that's the rule of thumb. And that depends on the stability of your system. But yes, with CW, we're able to, and time resolve as well, what about 1 micromolar change in oxy and deoxyhemoglobin.
There is one question online. How do you adjust the peer lambda limit in dense solutions?
The beer lambda, the beer?
Peer lambda limit in dense solutions.
I don't understand the question. Oh, okay, yes. So in FNIRS, people don't typically estimate the differential path length factor. They assume it's around 4, okay? That's when people do functional near-infrared spectroscopy. But in our hyperspectral NIRS, we can estimate the optical path length because, and actually what we do is we take the measurement and we fit it with a theoretical model. I didn't show it because I didn't want to have too much math there. But we fit with a theoretical model. So there are solution, analytical model of light propagation in different tissue type. So for instance, the brain can be approximated as an optically infinite, optically semi-infinite medium, which is very reasonable. Because if I put a light here, the likelihood of the light going anywhere here is very small. Obviously, no. So the light will be back reflected on this area, but if you look at the other area, light will not get there. So approximating, for instance, the brain as a semi-infinite medium is a good approximation. And then there are analytical solutions for that. You can model the brain as 3 layers, where you have the scalp, the skull, and the brain, or as a 2-layer, where you have the scalp and skull will be the top layer, and the bottom layer is the brain. And you use this model to fit your experimental data and estimate the concentration of these light absorbers in the tissue.
So thank you very much. It was a really great talk. So I don't know if I missed it or it's a valid question. So if you want to compare FNIR with MRI, so do they, I mean, in terms of resolution, in-depth imaging, the information that you get, how do they complement each other? Or, you know, if you just give us some comments that we see where we stand and how they scale.
Yeah, that's a good point, actually. You know, because the good thing for functional activation is that everything happens on the cortex. And both FNIRS and fMRI have access to the cortex. So it's a superficial layer of the brain. That's where all the activity happens. So that's why it's easy. And now with FNIRS, you have to have a system that is MRI compatible. And these big helmets, they are typically not MRI compatible. So the subject will do an experiment outside of the magnet, and they will go into the magnet and do another experiment, and they compare the two. That's why you have to have a large number of subjects, and you have to have fiducials so that you can do a registration, okay? So to make sure that, you know, you're comparing apple to apple, okay? That's basically how they do this. So question there?
Hello. I wanted to know if the method can be applied to animals too.
Sorry?
Can the method be applied to animals?
Oh, yeah. So for instance, the study I showed can be applied to animals. So basically what we do in my lab is that we start with simulations, when we have an idea, we start with simulation. And when we're done with the simulation, we sit down and we design the device we want to design. And then, because we are at the system level, we source the parts, put the system together, and then we do testing on tissue mimicking phantom. Okay, so these are ex vivo inert substances that mimic the optical properties of tissue. And once we're happy with that, then we move to the animal studies. So that's why I have a lab in the hospital. My lab in the hospital does the animal study. So we do the animal study where we validate our model. And these also have application in veterinary science, obviously. Okay? So we use this animal to validate our study, our devices, and before we go to human. In the same hospital, now when we finish in our lab, so our lab is on the first floor, we go to the 5th floor, that's where the humans are. And then we do this study in humans. So this system are applied in human. And we have also a system that we take in a different hospital, it's Victoria Hospital, that's where the Children's Hospital is located. That's where we do all our pediatric studies. Okay?
Okay, thank you for that insightful presentation, Prof. Mamadou. But I have a question on FNIR and FMIR. You mentioned that FNIRs are in general advantageous over FMIR, right?
Yeah.
So I just wanted to know, is this for all the applications or for this particular application? Is it for all the optical applications or for this particular application in medical physics?
Yeah, so fMRI, if you want to go look at the deep, something deep in the brain and so on, and the resolution of fMRI is better. If you go, because in fMRI you can go to high field and you have exquisite resolution that you cannot match with NIRS. You will not match with NIRS. But for certain application, for like looking at those applications I showed, the kids playing, interaction between two people, yeah, FNIRS is much better. Like if you want to do hyperscanning, which is scanning two people interacting with fMRI, you have to put one person in one scanner, another person in one scanner, and they see each other through a screen. That's not very interactive. So, but that's what people had before. But now, people have moved. Hyperscanning has become a very hot topic for people who used to do hyperscanning in fMRI. I think most of them are now moved to FNIR hyperscanning because it's so much more practical. Now, once you get some certain information, you can go back to fMRI for higher resolution. Each technique has its own niche.
Next, we have the last question because we have to go for lunch.
In your graph of absorption of the three colors, the first graph, I think, is oxyhemoglobin scatters red. All it absorbs it.
So if I correctly understand the question, so the question is that in the graph, first graph I saw the red was oxyhemoglobin. That is correct.
Okay, let's thank again the speaker. Before going for lunch, we have update information. Please, Harriet. For today, we have with Professor Pereira the experimental session at 2. Where is the place? You will in the lab. Okay. We have 3 groups of around 25 students. Harriet will inform you which students are in this group. And also we have a parallel, let's say, setting of the experiment with Alexia. As I understood, 2 students were selected for this today.
Yeah, the Sandra, is it? What is the name? Jane and
Sally.
Yeah, you were also Alessia plus Sankara from Masai Mara. So also tomorrow we will have poster session. Make sure that you have printed your poster, and also there is a list in the desk there. You indicate if you will present a poster. If you you have developed one and you had not indicated initially that you will be presenting a poster. Kindly, please. Thank you.
And the poster will be evaluated by a committee of, for the professors that are teaching you, then encourage to do your best presentation. For now, okay, we finish the section with the online. We stop for today. We invite you to the experimental section and those online for 2 more sections. And let's go for lunch. Thank you.
Good one. Tomorrow you will be, no? I think you are. I think we have to inform them about the group. Yes. We will go to the lab, but can you? From the list, let me say from the list, the first one to this is the first group. At 2, they go to. Okay, inform this. Yes. Yes. The list I will bring the list.
world challenges.
One notable thing about Multimedia University of Kenya is that it offers the resources for you to grow as a student.
And this is why I think it will be important for you to consider applying to the